Thousands of candidates study for AWS certifications every single day, yet a surprisingly small fraction can explain the deep architecture and mechanical trade-offs tested on the professional and specialty exams. If you are listening to this to prepare for your solutions architect professional, DevOps engineer professional, or security specialty certification, you already know that memorizing definitions will not get you a passing score. Professional exams demand that you think like a staff engineer, understanding the physical and logical constraints of the cloud from first principles. Today, we will dissect the entire AWS ecosystem service by service, ensuring you have the exact mental models required to ace your exams and design resilient, cost-effective architectures in the real world. Let us begin our deep dive by stripping away the abstraction layers and looking at the physical ground upon which the entire cloud is built. To design systems that pass professional certifications, you must understand the physical reality of the AWS Global Infrastructure. Many developers mistake the cloud for an abstract, virtual construct, but every byte of data and every cycle of compute runs on physical hardware housed inside concrete buildings, powered by local electrical grids, and connected by thousands of miles of fiber optic cables. The primary organizational unit of this infrastructure is the AWS region. A region is not a single data center. Instead, it is a fully isolated geographic area containing multiple, physically separated availability zones. When you deploy an application, selecting the appropriate region is your first and most critical architectural decision, guided by 4 key constraints: latency, compliance, service availability, and cost. Latency is governed by the physical distance between your servers and your users, because data cannot travel faster than the speed of light in fiber optic glass. Placing your servers in Europe to serve users in Asia introduces an unavoidable round-trip delay of over 100 milliseconds. Compliance is another driver, as strict data protection regulations, such as the European Union General Data Protection Regulation or HIPAA guidelines in healthcare, may legally prohibit you from storing citizen data on servers located outside political borders. Service availability also varies, as AWS introduces new compute hardware, custom silicon, and artificial intelligence features in a rolling fashion, meaning that the latest instance classes may only be available in primary regions initially. Finally, pricing differs between regions based on local land costs, local taxes, electricity rates, and network infrastructure costs, requiring architects to balance performance against operational budgets. Underneath the region layer, we find availability zones, commonly referred to as AZs. An availability zone is a logical grouping of one or more physical data centers. Each availability zone is engineered to be completely independent of the others in terms of power, water cooling, and network connectivity. This means they are connected to different electrical grids, sit on different floodplains, and are positioned away from major earthquake faults. The physical distance between availability zones within a region is carefully calculated. They are far enough apart that a single localized disaster, such as a flood, a severe storm, or a massive power outage, will not take down more than one availability zone. Yet, they are close enough, typically under 10 miles apart, to be connected by ultra-low latency, redundant private fiber optic networks. This physical proximity allows for synchronous replication of data between zones. When you write data to a highly available database, the primary instance can write to a standby instance in another availability zone and receive an acknowledgement in under 2 milliseconds. This dual nature of physical isolation and low-latency interconnection is what enables you to design fault-tolerant applications that survive the complete failure of an entire data center facility without the user ever noticing a disruption. To appreciate the scale and design of an availability zone, we must first examine the physical reality of the data center facility itself. A cloud data center is not merely a room filled with server racks. It is a highly engineered industrial facility designed for continuous, uninterrupted operation. AWS custom designs its data centers to maximize space, thermal efficiency, and physical security. Inside the facility, the server halls are organized to optimize airflow. Modern servers generate massive amounts of heat, and if this heat is not removed, components will fail within minutes. To prevent this, AWS uses a hot aisle and cold aisle configuration. Cool air is pumped into the cold aisles, pulled through the server chassis by internal fans, and exhausted into the hot aisles, where it is captured by containment systems and routed to cooling units. This physical separation of air streams dramatically reduces energy consumption and ensures that the processors operate within their optimal temperature ranges, even under maximum computational loads. Cooling these massive facilities requires robust water cooling systems that run on N+1 or even 2N redundancy. If a primary water pump or cooling tower fails, backup systems immediately activate to maintain the thermal balance. In regions with high ambient temperatures, AWS utilizes evaporative cooling, which uses the natural process of water evaporation to cool the air, consuming significantly less electricity than traditional mechanical refrigeration. The electrical infrastructure is similarly redundant. High-voltage utility lines enter the data center from multiple, physically separate routes to prevent a single traffic accident or construction incident from severing power. Inside the facility, the power is conditioned by uninterruptible power supplies, which use massive battery banks to bridge the gap between a utility failure and the activation of backup systems. If the utility grid fails completely, industrial-grade diesel generators start automatically, reaching full capacity within seconds. AWS maintains thousands of gallons of diesel fuel on site, along with priority fuel delivery contracts, ensuring that the data center can run independently for days during a catastrophic regional power grid collapse. To protect the physical integrity of these facilities, AWS implements multiple layers of physical access control. The perimeter of the data center is protected by security fences, vehicle barriers, and security officers patrolling the grounds. CCTV cameras monitor all entry points and server halls continuously. To enter the facility, employees and authorized visitors must pass through access control points that require multi-factor authentication, including biometric scans and security badges. Inside the facility, access to the server floors is restricted to hardware technicians who have been granted explicit, temporary authorization for specific maintenance tasks. All server racks are locked, and keys are managed using automated security key boxes that log every withdrawal and return. This physical security extends to the life cycle of the storage media. When a hard drive or solid-state drive inside an AWS data center reaches the end of its useful life, or if it fails, it cannot simply be thrown away. Because these disks store sensitive customer data, AWS enforces a strict chain of custody and destruction protocol. Failed disks are logically demagnetized or cryptographically wiped while still in the rack. Once removed, the disks are tracked using barcode scanners at every step of their journey to a high-security destruction room inside the facility. In this room, the disks are placed into industrial shredders that physically grind the platters and silicon chips into tiny fragments, ensuring that data recovery is physically impossible. This level of physical operational control is the foundation upon which all logical cloud security and compliance certifications are built. Connecting these isolated data centers to each other and to the rest of the world requires a massive private network infrastructure. AWS does not rely on the public internet to route traffic between its facilities. Instead, it operates a global, private fiber optic network that spans continents and oceans. This network utilizes redundant transit paths, including private undersea cables, to ensure that if a single cable is severed by an anchor or an earthquake, traffic is instantly rerouted over alternative paths without packet loss. Undersea cables emerge at landing stations, which are highly secure facilities that contain optical amplifiers and dense wavelength division multiplexing systems. This multiplexing technology allows a single pair of fiber optic glass to carry terabits of data per second by splitting light into multiple wavelengths. AWS manages these optical paths dynamically, adjusting routing tables in real time to bypass damaged cables and minimize latency. The network routers use anycast routing, which allows multiple physical servers to share a single IP address. When a user requests a resource, the network automatically routes the traffic to the physically nearest edge location or point of presence, reducing network latency and distributing the load across the global network. As the traditional boundaries of AWS regions and availability zones expand to meet the demands of edge computing and data sovereignty, new infrastructure options emerge. AWS local zones represent a significant step in this evolution. While a primary AWS region might be located in a suburban area with cheap land and power, a local zone brings compute, storage, and database services directly into major metropolitan areas. For instance, recent expansions have introduced local zones in metropolitan hubs like Istanbul and Hanoi, adding to a global footprint of over 30 metropolitan areas. Local zones are designed for workloads that require single-digit millisecond latency for local users, such as real-time financial trading, interactive gaming, or local media editing. From an architectural perspective, a local zone is treated as an extension of a parent region. You can orchestrate resources in a local zone using the same APIs and control planes, but the physical hardware is located closer to the urban center, communicating back to the parent region over high-speed, private AWS backbones. Another critical component of the modern edge infrastructure is AWS wavelength. While local zones target metropolitan centers, wavelength targets mobile devices and smart infrastructure connected to 5G networks. AWS installs physical racks of AWS hardware directly inside the data centers of telecommunications providers, right at the edge of their 5G networks. This removes the latency of routing traffic from a mobile device through the carrier network across the public internet and finally into an AWS region. By running containerized applications on EC2 instances inside a wavelength zone, developers can achieve latency of less than 10 milliseconds for mobile applications, enabling real-time logistics tracking, autonomous vehicle communication, and augmented reality processing. The key design pattern here is dividing your application architecture. You run the latency-sensitive presentation and real-time processing components in the wavelength zone, while maintaining your persistent databases, analytics pipelines, and heavy compute workloads in the main parent region. For workloads that cannot leave a customer's physical premises due to extreme security regulations, latency constraints, or massive local data volumes, AWS provides AWS Outposts. Outposts brings native AWS services, APIs, and operational models directly into your own on-premises data center or colocation facility. Second-generation Outposts racks feature modern compute instances, including M7i, C7i, and R7i, which deliver up to 40% better performance compared to older models. Furthermore, the networking architecture has been simplified, introducing more resilient self-service local gateways. This allows local workloads to communicate with on-premises resources at wire speed without relying on a connection to the parent region. Crucially, recent updates have brought third-party storage integrations to Outposts, allowing enterprise customers to hook up Outposts directly to their existing Dell PowerStore or HP Alletra MP arrays. This hybrid model guarantees that you can run services like Amazon ECS, EKS, and S3 locally on Outposts while keeping your data stored on your existing storage investments, all managed through a unified AWS console. Sovereignty and data control have become defining modern architectural requirements, leading to the creation of the AWS European Sovereign Cloud. This represents a physically and logically separate partition of AWS infrastructure located entirely within the European Union. Unlike standard global regions, the European Sovereign Cloud is operated, supported, and maintained exclusively by EU-resident AWS employees. This design provides public sector organizations and highly regulated industries with the confidence that all metadata, telemetry, and customer data remain strictly within European borders. When designing systems for this environment, architects must understand that this sovereign partition is logically isolated from the global AWS control plane. While you use the same APIs and development tools, you must architect your applications to run entirely within this boundary, managing identities, keys, and data replication independently of your global AWS accounts. Compliance with global security frameworks is a critical factor when selecting regions and designing cloud systems. AWS maintains compliance certifications across dozens of global standards, including ISO 27001, SOC1, SOC2, and SOC3 audits, Payment Card Industry Data Security Standard for financial transactions, and FedRAMP High Authorization for federal government workloads. These compliance frameworks impose strict requirements on physical security, logical partitioning, cryptographic key management, and administrative audit trails. For healthcare applications, AWS supports HIPAA compliance, enabling secure storage and processing of protected health information. Architects must verify that the target region and all selected services fall within the scope of the required compliance certifications. Utilizing AWS Artifact to download compliance reports and verify that the logical controls implemented in their applications satisfy regulatory requirements. To protect this massive global infrastructure, AWS operates under a fundamental security framework known as the Shared Responsibility Model. This model defines exactly where the security obligations of AWS end and where the security obligations of the customer begin. A common failure mode for junior engineers is assuming that because an application runs on AWS, it is automatically secure. The reality is that security is a partnership. AWS is responsible for the security of the cloud, which includes the physical security of the data centers, the concrete walls, the biometric access controls, the cooling systems, the physical hypervisors that partition virtual machines, and the underlying network routing tables. The customer, on the other hand, is responsible for security in the cloud. This means you are responsible for configuring your firewalls, defining IAM access permissions, patching your guest operating systems, encrypting your data both at rest and in transit, and managing your application code. Applying the shared responsibility model effectively requires architects to understand how the boundary of responsibility shifts across different service classes. In infrastructure as a service, such as Amazon EC2, the boundary is lowest. AWS manages the physical host and the virtualization hypervisor, while you manage the guest operating system, including security patches, application runtimes, network configurations, and data encryption. If you transition to a platform as a service model, such as Amazon RDS, AWS assumes responsibility for provisioning the virtual machine, patching the operating system, managing database updates, and setting up automated backups. Your responsibility is reduced to managing database user accounts, configuring access permissions, and optimizing query performance. Finally, in serverless or software as a service models such as Amazon S3, DynamoDB, or AWS Lambda, the operational responsibility shifts almost entirely to AWS. AWS manages the OS, the container runtime, the scaling mechanics, and physical storage replication. Your sole security responsibility is configuring IAM policies, enabling encryption options, and ensuring that access keys are securely stored. When utilizing hybrid deployments using AWS Outposts, the physical security of the hardware becomes a joint responsibility, where you must provide secure access and power to the rack while AWS manages the logical hardware lifecycle. Today, the shared responsibility model has been extended to address the unique challenges of generative AI, large language models, and agentic workflows. When you build applications using foundation models, such as the Amazon Nova family running inside Amazon Bedrock, the division of security responsibility shifts. AWS is responsible for securing the underlying model infrastructure, the secure execution environments, and ensuring that your training data is never used to train or improve the public foundation models. However, you, the customer, are responsible for the security of the inputs and outputs. You must implement guardrails to prevent prompt injection attacks, secure the vector databases that store your corporate knowledge, control access to the fine-tuned versions of your models, and monitor the autonomous decisions made by agentic systems. Understanding this division is critical not only for passing modern certifications but also for preventing catastrophic data leaks in production. To secure generative AI applications in production, you must implement tenant isolation and data protection patterns. When fine-tuning a model or using retrieval-augmented generation, your data is processed within an isolated memory environment allocated to your AWS account. This data must be encrypted at rest using customer-managed keys via AWS KMS and in transit using transport layer security. When data is retrieved from a vector database to augment a prompt, that database must sit within a private subnet, protected by security groups and network access control lists. The custom model weights generated during fine-tuning are stored in an AWS-managed repository isolated from other tenants, ensuring that your intellectual property is never exposed to other customers. Furthermore, you must configure Bedrock guardrails to filter out harmful content, detect personally identifiable information, and block prompt injections before they reach the model, completing your security obligations under the shared model. Let us explore how these infrastructure components dictate how we design for high availability and disaster recovery. A resilient system must be designed to survive failures at multiple levels of granularity. Individual disk failures, instance failures, availability zone failures, and entire region failures. To survive disk failures, we use network-attached storage with built-in redundancy, such as Amazon EBS. To survive instance failures, we use auto-scaling groups that automatically detect when a virtual machine stops responding and launch a replacement instance. To survive an availability zone failure, we design multi-AZ architectures, distributing our compute resources across multiple zones and using services like application load balancers to route traffic away from a degraded zone. Finally, to survive a catastrophic regional disaster, we design multi-region architectures, replicating data asynchronously across continental boundaries and using global traffic routing services like Amazon Route 53 or AWS Global Accelerator to failover traffic to a secondary region. When designing a disaster recovery strategy, you must define your recovery objectives, recovery time objective or RTO, and recovery point objective or RPO. RTO represents the maximum acceptable duration of downtime before your application is restored to service. RPO represents the maximum acceptable age of data that can be lost due to a disaster. Based on these metrics, you select from 4 primary disaster recovery patterns. The backup and restore pattern is the cheapest, involving periodic backups stored in S3 and replicated to a secondary region, with an RTO of hours and an RPO defined by your backup frequency. The pilot light pattern maintains a minimal version of your environment, such as your database replication standby, in the secondary region, provisioning compute resources only after a disaster is declared, bringing the RTO down to tens of minutes. The warm standby pattern runs a scaled-down but fully functional copy of your application in the secondary region, allowing faster failover by simply scaling up the running servers. Finally, the multi-site active-active pattern runs active workloads in both regions simultaneously, routing traffic using Route 53, delivering an RTO and RPO of near zero, but incurring significant cost and operational complexity. When designing these multi-region active-active systems, you must confront the fundamental trade-offs described by the CAP theorem and extended by the Paselk theorem. The CAP theorem states that in the event of a network partition, a distributed system can guarantee either consistency or availability, but not both. If you replicate data synchronously across regions to guarantee absolute consistency, your write operations will become extremely slow because the system must wait for the speed of light to carry the data across the ocean. If you replicate asynchronously to maintain low latency and high availability, you must accept eventual consistency, meaning that users in different parts of the world might see slightly different states of your application for a brief window. The Paselk theorem extends this by stating that even when there is no network partition, a system must trade off latency against consistency. As an elite architect, your role is to analyze these trade-offs, evaluate the business impact of data inconsistency, and select the appropriate replication strategy for each microservice in your stack, balancing user experience, latency, and business logic requirements. Ultimately, the AWS Global Infrastructure provides the physical foundation upon which all cloud systems are built. Whether you leverage the global reach of AWS regions, the low-latency urban presence of local zones, the 5G edge of wavelength, the hybrid footprint of outposts, or the isolation of the European sovereign cloud, the same architectural rules apply. You must design for fault isolation, enforce security boundaries under the shared responsibility model, and navigate the physical limits of speed and consistency. Establishing this structural mental model allows you to confidently approach the virtualization layers, beginning with the compute engines that drive application logic. Transitioning from physical infrastructure to the virtualization layer brings us to the compute layer. To design applications that run efficiently and scale to millions of users, we must understand the options, systems, and hardware platforms available within the AWS compute ecosystem. At the center of this ecosystem sits Amazon Elastic Compute Cloud, or Amazon EC2. EC2 allows you to provision virtual machines on demand, but behind the scenes, these virtual machines are run on massive physical host servers. The core technology that enables this virtualization with minimal overhead is the AWS Nitro system. Historically, traditional hypervisors had to allocate a significant portion of the physical host CPU and memory to manage virtual machine networks, local storage volumes, security policies, and hypervisor management. This overhead reduced the compute power available to the customer's virtual machine. The Nitro system completely changed this paradigm by offloading all network, storage, security, and management tasks onto dedicated hardware cards, known as Nitro cards. By taking these operational tasks away from the main host CPU, AWS can deliver virtual machines that provide near bare metal performance, reserving 100% of the physical host CPU and memory for the customer. To understand the architecture of the Nitro system, we must examine its distinct hardware components. The system consists of multiple PCI Express cards that connect to the main host motherboard. The Nitro card for VPC offloads the virtual private cloud network routing, security group evaluation, and network address translation from the host CPU. This allows for high-speed network performance, reducing latency and packet overhead. The Nitro card for EBS offloads all block storage operations, executing local encryption and compression algorithms in hardware, which guarantees consistent throughput to network-attached storage volumes. The Nitro card for storage offloads local NVMe storage operations, optimizing access to local solid-state drives. The Nitro security chip is embedded directly on the motherboard, preventing unauthorized modifications to the system firmware and establishing a hardware root of trust. Finally, the Nitro hypervisor is a lightweight, low-overhead software component that partitions memory and CPU resources without managing complex networking or storage stacks. This disaggregated architecture ensures that when you run a virtual machine on EC2, you receive the full performance of the hardware you pay for, with zero virtualization overhead. For applications requiring extreme security isolation when processing highly sensitive datasets, such as personally identifiable information, financial records, or cryptographic keys, the Nitro system supports Nitro enclaves. A Nitro enclave is an isolated, highly secure compute environment carved out of a parent EC2 instance. When you launch a Nitro enclave, the Nitro hypervisor partitions a designated amount of CPU and memory from the host, isolating it completely from the parent instance. The enclave has no persistent storage, no network connectivity, and no interactive operator access, which means even the root user of the parent EC2 instance cannot log in or view the data inside the enclave. Communication between the parent instance and the enclave is restricted to a local virtual socket or SOC interface. To verify the software running inside the enclave, the system utilizes cryptographic attestation. The Nitro hypervisor generates an attestation document signed by the hardware root of trust, containing measurement hashes of the enclave image, the kernel, and the application code. Your application can present this attestation document to external services, such as AWS KMS, to prove its identity and securely retrieve decryption keys, ensuring that sensitive data is only processed by verified, tamper-proof code. To optimize the physical placement of your EC2 instances on the underlying hardware racks inside a data center, you can configure placement groups. Placement groups support three main topologies: cluster, spread, and partition. A cluster placement group packs instances close together within a single availability zone. This topology delivers low-latency network performance and high throughput, making it the ideal choice for high-performance computing, distributed database clusters, and rapid node synchronization. A spread placement group places instances on physically separate hardware racks, each with its own independent power and network sources, ensuring that a hardware rack failure will not take down more than one instance in the group, which is appropriate for small fleets of critical virtual machines. A partition placement group divides your instances across multiple logical partitions, where instances in one partition do not share hardware racks with instances in other partitions. This topology is designed for large-scale, distributed workloads like Hadoop, HDFS, or Cassandra, where partitions isolate data replicas from physical hardware failures. Furthermore, to prevent network bandwidth contention, you should use EBS-optimized instances, which establish a dedicated connection channel for network-attached storage traffic, separating block storage read and write paths from standard network interfaces. For workloads that experience long startup times due to application initialization, database preloading, or memory caching, EC2 supports hibernation. When you hibernate an instance, EC2 saves the contents of the physical RAM to your root EBS volume, shuts down the guest operating system, and terminates the instance compute allocations. When you start the instance again, EC2 restores the RAM state from the EBS volume and resumes the operating system boot process, bypassing the application initialization phase. This reduces application startup times from minutes to seconds, allowing latency-sensitive workloads to scale up quickly in response to traffic spikes. Modern compute architectures have reached new levels of performance and efficiency with the introduction of the AWS Graviton 5 processor. Running on the 6th generation Nitro system, Graviton 5 powers general-purpose and storage-optimized instance families, delivering significantly improved compute performance. This custom silicon features 192 cores per chip, which doubles the core density of older generations and incorporates high-speed memory interfaces and peripheral component interconnect Express Generation 6. For software architects, this means Graviton 5 delivers up to 25% better compute performance compared to the previous generation, making it the default choice for heavy database workloads, containerized applications, and distributed caching systems. Furthermore, the 6th generation Nitro system introduces the Nitro Isolation Engine, a formally verified separation kernel designed directly into the Nitro hardware. This isolation engine provides mathematically provable isolation between virtual machines, preventing side-channel attacks and raising the security bar for multi-tenant cloud environments. When selecting an EC2 instance, you must choose from a variety of instance families tailored for different workloads. General-purpose families provide a balanced ratio of CPU to memory, making them ideal for web servers and small application backends. If you are running memory-intensive workloads, such as in-memory databases, large-scale caching layers, or real-time analytics engines, you will choose memory-optimized families. For compute-heavy tasks like high-performance computing, video encoding, or batch processing, the compute-optimized families offer a higher CPU-to-memory ratio. When your application requires massive local storage throughput, such as distributed file systems or transactional databases, The storage-optimized families provide ultra-fast local solid-state drives. Finally, for specialized artificial intelligence and machine learning tasks, accelerated computing families and dedicated Trainium instances provide high-performance hardware acceleration. For example, compute instances leveraging the latest graphics processing units are optimized for heavy training workloads, while dedicated Trainium instances provide cost-effective, custom-designed AWS silicon for deep learning model training and inference. Beyond basic instance types, a crucial aspect of EC2 architecture is the pricing model, which directly dictates your cost optimization strategy. On-demand instances are billed per second and require no long-term commitment, making them perfect for unpredictable workloads or short-term testing. Spot instances offer massive savings compared to on-demand pricing by allowing you to bid on spare AWS capacity. However, the trade-off is that AWS can reclaim these instances with only a 2-minute warning when the capacity is needed elsewhere. Therefore, spot instances are only suitable for fault-tolerant, stateless, or batch processing applications. For predictable, steady-state workloads, you should use reserved instances or savings plans. A savings plan requires a 1-year or 3-year commitment to a consistent amount of compute usage, measured in dollars per hour, and offers deep discounts. The architectural pattern here is to construct a hybrid compute fleet. Use savings plans to cover your baseline, continuous compute needs. Use auto-scaling with on-demand instances to handle unexpected traffic spikes. And use spot instances for asynchronous background processing jobs. While EC2 virtual machines provide full control over the guest operating system and kernel configuration, modern application design has shifted heavily toward containerization. To manage these containers at scale, AWS offers 2 primary orchestrators: Amazon Elastic Container Service, or ECS, and Amazon Elastic Kubernetes Service, or EKS. ECS is a highly opinionated AWS native container orchestrator. It is deeply integrated with other AWS services out of the box, such as IAM, CloudWatch, and application load balancers, making it simple to deploy, secure, and monitor containerized microservices. EKS, on the other hand, is a fully managed Kubernetes service. It maintains strict compatibility with upstream Kubernetes APIs, allowing you to run standard Kubernetes manifests and integrate with the open-source cloud-native ecosystem. EKS clusters consist of the managed control plane and worker nodes, which can be configured as self-managed nodes, managed node groups, or serverless Fargate profiles. To automate node scaling and optimization on EKS, you can utilize Carpenter. Carpenter is a high-performance, open-source Kubernetes autoscaler that bypasses traditional cluster autoscaling scaling delays. Carpenter evaluates pod scheduling constraints and resource requests directly, provisioning the most cost-effective and appropriately sized EC2 instances dynamically, and consolidates nodes when workloads scale down, reducing compute waste. Regardless of whether you choose ECS or EKS, you must decide how to provision the compute hardware that runs your containers. You can run containers on self-managed EC2 instances, which gives you complete control over the underlying host configuration, custom kernels, and local disk volumes. However, this requires you to manage, patch, and scale the host operating system. To eliminate this operational burden, AWS provides AWS Fargate, a serverless compute engine for containers. When you run containers on Fargate, you do not provision or manage virtual machines. Instead, you simply specify the CPU and memory requirements for each container and AWS provisions and manages the underlying host dynamically. Fargate isolates each container task in its own single-use micro-VM, ensuring a high security boundary. From an architectural perspective, Fargate shifts the responsibility of host operating system patching, scaling, and hypervisor security to AWS, allowing your developers to focus entirely on building application logic. When containerizing microservices, understanding container networking is critical for security and performance. In Amazon ECS, the standard networking mode is the OSPF mode. When a task is launched in OSPF mode, ECS provisions a dedicated Elastic Network Interface, or ENI, from your VPC subnet and assigns it a private IP address directly. This task-level IP address allows you to apply VPC security groups directly to individual tasks, rather than applying them to the underlying EC2 container instance. In contrast, older networking modes like Bridge or Host share the container instance network interface, requiring you to manage complex port mappings and exposing host-level ports to the network. In Amazon EKS, networking is managed by the VPC Container Network Interface, or VPC CNI plugin. The VPC CNI plugin allocates IP addresses from your VPC subnets directly to Kubernetes pods, enabling pods to communicate directly with other VPC resources without network address translation overhead. This native integration allows pods to utilize security groups for pods, applying granular firewall rules directly to Kubernetes deployments and simplifying network auditing. For web applications and APIs that do not require the full complexity of a container orchestrator, AWS offers AWS App Runner. App Runner is a fully managed service that takes your source code or container image and deploys it directly as a web service with a public URL. It automatically handles load balancing, transport layer security encryption, auto-scaling, and secure deployment pipelines. Under the hood, App Runner orchestrates the containers on Fargate and routes traffic using AWS Managed Application Load Balancers. This makes it an ideal solution for front-end services, back-end API microservices, or rapid prototyping where you want to minimize your infrastructure configuration and deploy code with a single command. At the far end of the serverless spectrum lies AWS Lambda, which represents the function-as-a-service model. Lambda allows you to run code without provisioning or managing any servers. Instead of running a continuous process that waits for incoming requests, Lambda is entirely event-driven. It runs your code only when triggered by an event, such as an HTTP request through API Gateway, a file upload to S3, a message arriving in an SQSQ, or a state transition in a step function. Lambda scales your functions horizontally, spinning up separate execution environments to handle concurrent requests. This means that if 1,000 users hit your API at the exact same millisecond, Lambda will spin up 1,000 parallel environments to process the requests simultaneously, and then scale back down to 0 when the traffic subsides, billing you only for the exact milliseconds your code runs. To design efficient serverless architectures, we must understand the life cycle of a Lambda execution environment. When a Lambda function is triggered for the first time, or after a configuration change, the service must perform what is called a cold start. During a cold start, Lambda allocates the necessary compute resources using micro-VMs, downloads your function code from S3, initializes the runtime environment, and executes your function initialization code outside the main handler. This initialization process can take anywhere from a few hundred milliseconds to several seconds, depending on the size of your deployment package and the runtime language. Java and .NET runtimes typically suffer from longer cold starts than lightweight runtimes like Node.js, Python, or Go. Once the function executes, Lambda keeps the execution environment warm for a period of time, typically around 5 to 15 minutes. If another event triggers the function during this window, Lambda reuses the warm environment, bypassing the initialization phase. This is known as a warm start, which typically executes in single-digit milliseconds. Architects can mitigate the latency impact of cold starts using several key strategies. First, keep your deployment package as small as possible by only importing the specific SDK libraries and dependencies your code needs, rather than importing the entire SDK. Second, optimize your initialization code. Place tasks that only need to run once, such as establishing database connections, loading configuration parameters, or initializing clients, outside the main Lambda handler function. This ensures they run during the initialization phase and can be reused during warm starts. Third, for latency-critical APIs where cold starts are unacceptable, you can configure provisioned concurrency. This feature tells AWS to pre-allocate a specific number of warm execution environments, guaranteeing that requests are always routed to warm environments, thus eliminating cold start latency entirely. However, provisioned concurrency incurs a continuous hourly charge, representing a trade-off between absolute latency guarantees and serverless cost optimization. To eliminate cold start latency for Java-based serverless applications, AWS provides Lambda SnapStart. When you enable SnapStart on a Lambda function version, the service executes the complete initialization phase during the deployment process. Once the initialization completes, SnapStart takes a cryptographic snapshot of the Firecracker micro-VM memory and disk state, encrypting it and storing it in a high-speed cache. When the function is triggered for the first time, Lambda restores the execution environment directly from the cache snapshot, bypassing the class loading and object initialization steps. This reduces cold start times for Java runtimes from several seconds to sub-second levels, enabling enterprise developers to run Java workloads in latency-critical API pathways without incurring the continuous cost of provisioned concurrency. A critical capability of AWS Lambda, especially important in the era of generative AI, is streaming responses. Historically, Lambda functions had to buffer the entire execution output in memory and return it in a single payload, which was limited to 6 megabytes. If your code generated a large file or streamed tokens from a language model, the client had to wait for the entire process to finish. With response streaming, Lambda can start sending chunks of data back to the client as they are generated by your code. This reduces the time to first byte latency, enabling real-time text generation interfaces, dynamic media rendering, and the processing of payloads larger than the traditional 6 megabyte limit. Lambda also supports custom runtimes using Lambda layers and Lambda extensions, which allow you to package custom binaries, libraries, and monitoring tools separately from your function code, standardizing developer runtimes across an enterprise organization. When choosing between these compute paradigms, you must analyze your workload constraints carefully. EC2 is the optimal choice when you need full control over the operating system, specialized kernel modules, persistent local file systems, or when running legacy applications that cannot be containerized. ECS and EKS are ideal for containerized microservice architectures with steady-state workloads, complex network routing requirements, or when migrating existing container workloads from on-premises environments. AWS Lambda is best suited for unpredictable, event-driven, or intermittent workloads where you want to minimize operational overhead and pay only for active execution time. By mapping your application requirements to the strength of each compute option, you can construct a resilient, high-performance, and cost-effective compute layer that serves as the engine of your cloud architecture. With this complete understanding of compute, we are ready to examine the storage systems that persist your application data. Persisting your data securely, reliably, and at scale brings us to the storage layer. A common trap for developers is assuming that a single storage technology can fit every application need. The reality is that AWS offers a wide array of storage services, each optimized for different data models, access patterns, and cost constraints. To design high-performance architectures, you must master the differences between object storage, block storage, and file storage, and understand how to tier your data to balance performance and budget. Let us begin our exploration with Amazon Simple Storage Service, commonly known as Amazon S3, which represents the standard for cloud-scale object storage. S3 is designed to store flat, unstructured data of virtually unlimited size. In S3, data is organized into buckets, which are logical containers and stored as objects. Each object consists of a key, which is its unique identifier path, a value, which is the raw data byte sequence, metadata, which describes the object properties, and optionally a version identifier. For latency-critical applications that need ultra-fast object storage, AWS has introduced Amazon S3 Express One Zone. Unlike standard S3, which distributes your data across at least 3 availability zones, S3 Express One Zone stores your data in a single availability zone. This storage class organizes data in a new type of bucket called a directory bucket. By co-locating the data in the same availability zone as your compute resources, S3 Express One Zone delivers single-digit millisecond latency, which is up to 10 times faster than S3 standard, while reducing API transaction costs by up to 50%. This makes S3 Express One Zone the ideal choice for high-throughput, low-latency tasks such as AI and machine learning model training, real-time analytics engines, and high-frequency financial batch processing. However, because it stores data in a single zone, you must accept the risk that a failure of that specific availability zone would result in data loss unless you implement replication to a secondary bucket in a different zone. To simplify data lake architectures, AWS provides Amazon S3 table buckets. S3 table buckets are a specialized bucket type optimized for structured, tabular data. They provide native support for the open-source Apache Iceberg table format, allowing you to run analytical queries directly on your S3 data without the operational overhead of manually managing files. S3 table buckets automatically handle maintenance tasks such as compaction, which merges small files into larger ones to improve query speed, snapshot pruning, and orphan file cleanups. By using S3 table buckets, you can build high-performance data lakes where analytical engines like Athena or Redshift can query data with lower latency and lower transaction costs, treating S3 not just as a dump of raw files, but as a fully managed table storage engine. When uploading massive files to S3, you must use multi-part uploads. Multi-part upload allows you to break a single large file into smaller parts and upload them concurrently to S3, reducing upload times and handling network interruptions by retrying individual failed parts. S3 requires multi-part uploads for files larger than 5 gigabytes and recommends them for files larger than 100 megabytes. The minimum part size is 5 megabytes except for the last part. If a multi-part upload is initiated but never completed or aborted, the uploaded parts remain in the bucket, accumulating storage costs. To prevent this financial leak, you configure S3 lifecycle policies to automatically delete incomplete multi-part uploads after a specified number of days, optimizing storage efficiency. To replicate data across buckets for geographical distribution or compliance, S3 supports same-region replication, or SRR, and cross-region replication, or CRR. Replication requires versioning to be enabled on both the source and destination buckets. SRR is ideal for consolidating logs or syncing development environments within a region, while CRR replicates data across different regions to support disaster recovery plans. To secure a SLA for replication latency, S3 Replication Time Control, or RDC, guarantees that 99% of new objects are replicated within 15 minutes, providing a predictable replication window. Replication automatically maintains object metadata, tags, and ACLs, and can be configured to replicate KMS encrypted objects, transferring possession of encryption keys securely. For event-driven architectures, you can configure S3 event notifications. Event notifications publish messages when specific actions occur in your bucket, such as object creation, deletion, or restoration from archive tiers. You can route notifications directly to destinations like SQS, SNS topics, or Lambda functions, triggering automated processing pipelines as files arrive. Furthermore, S3 integrates natively with Amazon Event Bridge, allowing you to route object events to third-party APIs or complex serverless workflows. To audit storage metrics and configurations, S3 Inventory provides daily or weekly reports on object configurations, encryption status, and replication compliance, replacing expensive list API calls for large-scale data lakes and big data pipelines. For standard object storage workloads, S3 offers a variety of storage classes that let you optimize costs based on how frequently your data is accessed. S3 Standard is the default class, designed for active, frequently accessed data. For data that is accessed less often but still requires sub-millisecond retrieval, S3 Standard Infrequent Access and S3 Zone Infrequent Access offer lower storage costs but charge a retrieval fee per gigabyte. If your data access patterns are unpredictable or fluctuate over time, you should use S3 Intelligent Tiering. Intelligent tiering automatically monitors your access patterns and moves your data between two main access tiers: a frequent access tier and an infrequent access tier. Intelligent tiering has been expanded with deeper archiving tiers that can automatically move cold data to archive or deep archive states after long periods of inactivity. The primary benefit of intelligent tiering is that it has no retrieval fees and requires zero operational overhead, making it the most cost-effective choice for general-purpose application storage where you cannot predict user access behaviors. For long-term preservation of cold data that is rarely accessed, you will choose from the Amazon S3 Glacier storage classes. Glacier Instant Retrieval provides millisecond access for data that must be retrieved instantly, but is only accessed a few times a year. Glacier Flexible Retrieval, formerly known as Glacier Standard, offers retrieval times ranging from a few minutes using expedited retrieval to 3 to 5 hours using standard retrieval. For the absolute lowest storage cost, Glacier Deep Archive stores data that you might access once or twice a year, returning it within 12 hours. When designing an archiving system, you can use S3 lifecycle policies to automate the transition of data between these classes. For example, you can write a policy that moves objects from S3 standard to S3 standard IA after 30 days, then to Glacier flexible retrieval after 90 days, and finally deletes the objects after several years. This automated tiering ensures you are never paying premium storage rates for stale data. Beyond cost optimization, S3 includes robust security features to protect your data at rest and in transit. By default, all new buckets encrypt data at rest using server-side encryption with AWS managed keys. For greater control over key rotation and access policies, you can use server-side encryption with customer-managed keys via AWS KMS. To protect against accidental deletions or malicious overwrites, you should enable S3 versioning, which stores every iteration of an object under the same key. When versioning is enabled, you can also configure multi-factor authentication delete, requiring physical MFA credentials to permanently delete an object version. For regulatory compliance, S3 Object Lock allows you to store objects using a write-once-read-many, or WORM model. S3 Object Lock supports two retention modes. Compliance mode, where no user, including the root account, can shorten the retention period or delete the objects. And governance mode, where specific users with special IAM permissions can override the lock. You can also apply legal holds, which block object deletion indefinitely until the hold is manually removed, providing mathematical guarantees of data integrity. To manage access permissions for large shared buckets, you can configure S3 access points. An access point is a unique network endpoint with its own dedicated lifecycle and IAM policy, allowing you to define distinct access controls for different developer groups or applications accessing the same S3 bucket, preventing the need to manage complex, multi-thousand-line bucket policies. While S3 provides object storage, virtual machines require block storage to run operating systems and mount file systems. This is the role of Amazon Elastic Block Store, or EBS. An EBS volume behaves like a physical hard drive or solid-state drive that you connect to a single EC2 instance. All new and existing provisioned IOPS volumes, known as IO2, are processed as IO2 Block Express volumes by default. Designed for mission-critical, I/O heavy workloads like SAP HANA, Oracle, and Microsoft SQL Server databases, IO2 Block Express volumes deliver up to 256,000 input-output operations per second, 4,000 megabytes per second of throughput, and up to 64 terabytes of capacity per volume, all with sub-millisecond latency and high durability. For general-purpose workloads, GP3 volumes remain the standard, providing a cost-effective balance of performance and price. Crucially, GP3 allows you to provision performance features like IOPS and throughput independently of the volume size. This means you can create a small 100 gigabyte volume and scale its performance to handle spikes in traffic without being forced to pay for unused storage capacity, which was a major limitation of older volume types. For workloads requiring shared block storage, EBS supports multi-attach. This feature allows you to attach a single provisioned IOPS volume to multiple EC2 instances simultaneously within the same availability zone. To utilize multi-attach safely, you must run a cluster-aware file system on the instances, such as GFS2, which coordinates write operations and prevents data corruption. EBS support dynamic volume modification, allowing you to increase volume size, change volume type, and scale provision performance properties on the fly without detaching the volume or shutting down the virtual machine, waiting for optimization cycles to complete in the background. To share file storage across multiple compute instances, you must use file storage services. Amazon Elastic File System, or EFS, provides a serverless, fully elastic file system that supports the standard network file system version 4 protocol. Unlike EBS, which can only be attached to a single EC2 instance in a single availability zone at a time, EFS can be mounted simultaneously by thousands of compute instances, including EC2 virtual machines, container tasks in ECS or EKS, and even serverless AWS Lambda functions. EFS automatically scales its storage capacity up and down as you add and remove files, meaning you do not need to provision storage in advance. It distributes your data across multiple availability zones by default, providing high durability and availability. EFS supports standard and infrequent access storage classes, and you can enable EFS lifecycle management to transition inactive files to EFS IA or EFS archive tiers, optimizing storage costs. You configure EFS throughput using Elastic Throughput Mode, which automatically scales performance capacity in response to read and write workloads, charging you only for the throughput consumed. This makes EFS the primary choice for shared application storage, content management systems, and development home directories where multiple workers need simultaneous read and write access to a shared directory. EFS mounts require mount targets to be configured in each availability zone where compute instances reside, routing traffic over port 2049 and applying IAM authorization policies to govern connections. For workloads that require specialized file systems, Amazon FSx provides fully managed, high-performance file systems tailored for specific operating systems and storage engines. FSx for Windows File Server provides native Windows storage with full support for the Server Message Block Protocol, Microsoft Active Directory integration, and Windows Access Control Lists. FSx for Lustre is a high-performance file system designed for compute-intensive workloads like high-performance computing, financial modeling, and machine learning training, delivering millions of IOPS and sub-millisecond latencies by piping data directly from S3. FSx for NetApp ONTAP allows enterprise customers to migrate their on-premises NetApp workloads to AWS without rewriting their storage administration scripts, supporting deduplication, compression, thin provisioning, and NetApp SnapMirror replication to synchronize data across hybrid storage. Finally, FSx for OpenZFS offers a high-performance open-source file system. FSx for OpenZFS has been enhanced with an intelligent tiering storage class that automatically moves inactive files to cheaper storage tiers, saving up to 85% on SSD storage costs. It also supports on-demand replication across regions and S3 access points, allowing cloud services to read and write directly to your OpenZFS volumes. To bridge the gap between your on-premises data centers and the AWS storage cloud, AWS provides AWS Storage Gateway. Storage Gateway is a hybrid cloud storage service that lets you connect local software appliances to AWS storage repositories. It is deployed as a virtual machine in your local environment, presenting standard storage protocols to your local applications. Comes in 3 main configurations. File Gateway allows local clients to write files to a local network share, which the gateway automatically translates and uploads as objects in S3. Volume Gateway provides local block storage volumes backed by S3, caching frequently accessed data locally to maintain low latency. Tape Gateway replaces physical tape backup systems, allowing your existing backup software to write to a virtual tape library backed by S3 Glacier. By using Storage Gateway, you can leverage the infinite scale and low cost of AWS storage without having to modify your existing on-premises software workflows. In summary, selecting the right storage architecture is a balancing act between access speed, durability, shared access capability, and cost. If you need global, infinite-scale, event-driven storage for files, S3 is your default choice, leveraging Express One Zone for extreme low-latency applications and table buckets for iceberg data lakes. When your databases require dedicated, sub-millisecond block storage for virtual machines, you will choose EBS, using IO2 Block Express for maximum performance and GP3 for general workloads. If you need a shared, POSIX-compliant file system across multiple zones and thousands of compute units, EFS is the optimal tool. For enterprise-grade file systems like Windows DFS, Lustre, NetApp ONTAP, or OpenZFS, the FSX family provides tailored, high-performance solutions. With this complete understanding of storage mechanisms, we are prepared to explore the CDN and networking services that accelerate data access globally. Accelerating data delivery and managing network paths brings us to the content delivery network and networking layers. For global applications, delivering a low-latency user experience requires you to cache content close to your users and optimize data paths across the global internet. To understand these optimization paths, we must first establish how networks are logically partitioned and routed inside AWS. At the center of this networking ecosystem is the Amazon Virtual Private Cloud, commonly known as a VPC. A VPC allows you to define a logically isolated virtual network within your AWS account. When you create a VPC, you must assign it a classless interdomain routing block or CIDR block, which defines the range of private IP addresses your resources can use. The standard recommendation is to use private IP ranges defined by RFC 1918, such as the 10.0.0.0/16 block, which provides up to 65,536 IP addresses. Inside this VPC, you partition your network into subnets. A subnet is a segment of the VPC IP range associated with a specific availability zone. It is crucial to understand that subnets cannot span multiple availability zones. This physical constraint ensures that if an availability zone fails, only the resources in that specific subnet are affected, preserving fault isolation. VPCs support both IPv4 and IPv6 network protocols, allowing you to configure dual-stack VPCs. IPv6 addresses are globally unique public addresses, meaning you do not use private IP spaces or network address translation for IPv6 communication. To allow instances in private subnets to make outbound IPv6 connections while blocking incoming internet traffic, AWS provides egress-only internet gateways. An egress-only internet gateway is stateful, allowing return packets from outbound queries but preventing external systems from initiating connections to your private resources, functioning as a free-of-charge outbound gateway for IPv6 traffic. When routing traffic within a VPC, the local router evaluates route tables associated with your subnets. Every route table contains a default local route that enables communication between all subnets in the VPC. The router utilizes the longest prefix match algorithm to determine the destination for each packet. This algorithm evaluates all matching routes in the table and selects the rule with the most specific subnet mask, ensuring that targeted traffic, such as private service endpoint routing, takes precedence over broader default paths. To propagate routes automatically from virtual private gateways or direct connect links, you can enable route propagation in the route tables, automating BGP routing updates. When you create a subnet, AWS automatically reserves 5 IP addresses within the range. For instance, in a 24 subnet, which contains 256 IP addresses, only 251 are available for your resources. AWS reserves the first IP address for the network router, the second for the domain name system server, the third for the network time protocol provider, the fourth for future capability, and the last IP address for the network broadcast address. Subnets are classified as either public or private based on how they route traffic to the external internet. A public subnet is associated with a route table that contains a default route directing traffic to an internet gateway. An internet gateway is a horizontally scaled, highly available virtual appliance that performs static network address translation, mapping private IP addresses of your instances to public IP addresses so they can communicate with public web servers. Conversely, a private subnet has no direct route to the internet gateway. To allow instances in private subnets to download security updates or communicate with external APIs without exposing them to inbound connections, you must use a Network Address Translation Gateway, or NAT gateway. A NAT gateway must be deployed inside a public subnet, and you must update the route tables of your private subnets to route outbound traffic through this gateway. The NAT gateway translates the private IP addresses of your instances into its own elastic IP address, forwards the requests to the internet, and routes the response packets back. From an architectural perspective, you should deploy a NAT gateway in each availability zone where you have private subnets. If you deploy a single NAT gateway in a single zone and share it across all subnets, a failure of that specific zone will sever internet access for your entire VPC, violating high availability design principles. Furthermore, NAT gateways charge both an hourly rate and a data processing fee per gigabyte, meaning that running massive data transfer operations through a NAT gateway can quickly inflate your billing costs, representing a significant architectural trade-off that requires careful data path optimization. Securing the traffic moving within your VPC requires a clear understanding of the difference between stateless network access control lists, or NACLs, and stateful security groups. A security group acts as a virtual firewall that controls traffic at the individual resource or elastic network interface level. Security groups are stateful, meaning that if you define an inbound rule allowing traffic on port 80, the response traffic from your instance back to the client is automatically allowed, regardless of your outbound rules. Security groups only support allow rules, and they evaluate all rules in their configuration before making a decision. In contrast, network access control lists operate at the subnet boundary and are stateless. This means that if you allow inbound traffic on port 80, you must explicitly write an outbound rule to allow the return traffic on the ephemeral port range, which typically spans ports 10,248 to 65,535. NACLs support both allow and deny rules, and they evaluate rules in numerical order, stopping at the first match. This makes NACLs the appropriate tool for blocking specific IP addresses or implementing broad network boundaries before traffic reaches your application servers. Connecting separate VPCs requires selecting the appropriate routing architecture. VPC peering establishes a direct network connection between two VPCs, allowing resources to communicate using private IP addresses as if they were on the same network. However, VPC peering is non-transitive, meaning that if VPC-A is peered with VPC-B, and VPC-B is peered with VPC-C, VPC-A cannot communicate with VPC-C through VPC-B. As the number of VPCs in an organization grows, managing a web of peering connections becomes operationally complex. To solve this, AWS Transit Gateway acts as a cloud router, establishing a hub-and-spoke network topology. By attaching all your VPCs, VPNs, and direct connect connections to a single transit gateway, you can centralize your routing tables and security policies. Transit Gateway utilizes route table associations to link attachments to specific route tables and route table propagations to dynamically publish network routes. Platform teams can isolate traffic domains by configuring separate transit gateway route tables, routing traffic through centralized inspection VPCs containing AWS network firewalls using Transit Gateway Appliance Mode, which preserves traffic symmetry across multiple zones. Transit Gateway integrates with AWS organizations using Resource Access Manager, allowing you to share the Transit Gateway across multiple AWS accounts, which simplifies multi-account networking architectures. To secure and private link services within your virtual private cloud without exposing them to the public internet, you must use VPC endpoints. VPC endpoints are virtual devices that connect your VPC to supported AWS services and VPC endpoint services. They come in two configurations: interface endpoints, powered by AWS Private Link, provision elastic network interfaces inside your private subnets with private IP addresses. They use DNS routing to direct traffic to the destination service and can be secured using security groups. Gateway endpoints, on the other hand, do not use network interfaces or private IPs. Instead, they update your subnet route tables to direct traffic directly to S3 or DynamoDB. Gateway endpoints are free of charge, whereas interface endpoints incur an hourly rate and a data processing charge. Utilizing VPC endpoints is a fundamental security requirement for high-compliance environments, ensuring that traffic between your application and AWS services never traverses the public internet. To accelerate content delivery globally, the core service is Amazon CloudFront, a global content delivery network service. CloudFront works by caching content at edge locations worldwide. When a user requests a file, such as a video, an image, or a static web page, CloudFront routes the request to the nearest edge location. If the content is cached, it is delivered instantly. If not, CloudFront fetches the content from the origin, such as an S3 bucket or an application load balancer, and caches it at the edge for future requests. To optimize origin performance and protect host databases from traffic spikes, CloudFront supports Origin Shield. Origin Shield acts as a centralized caching layer that sits between regional edge caches and your origin, consolidating requests to maximize cache hit ratios and minimize origin load. To secure S3 origins, CloudFront utilizes Origin Access Control, which ensures that users cannot bypass the content delivery network and access your S3 buckets directly, forcing all requests to go through CloudFront where they can be inspected, optimized, and authenticated. Managing edge behaviors requires architects to configure cache policies and origin request policies. A cache policy defines what parameters, such as query strings, headers, or cookies, are included in the cache key, determining when CloudFront can serve a cached response and when it must forward the request to the origin. An origin request policy defines what headers or cookies from the incoming request are forwarded to the origin without affecting the cache key. CloudFront supports automatic file compression using gzip and Brotli algorithms, reducing file sizes during transit to accelerate load times. To customize content at the edge in real time, CloudFront offers two options: CloudFront Functions and Lambda at Edge. CloudFront Functions is a lightweight, JavaScript-based execution environment optimized for high-volume, latency-sensitive tasks like URL redirection, header manipulation, and token validation. These functions run at the edge locations in sub-milliseconds and execute on viewer request and viewer response events. Lambda at Edge, on the other hand, is a full Node.js or Python environment running at regional edge caches, capable of executing complex processing logic, network requests, and database calls on all four lifecycle events: viewer request, origin response, and viewer response. The architectural trade-off here is execution cost and latency. Use CloudFront functions for simple header tweaks and URL rewriting, and use Lambda at Edge for dynamic database integrations, content generation, and third-party API queries. Pricing for CloudFront can be managed via flat-rate pricing plans, which provide predictable costs for high-volume operations. These plans can include support for Lambda at Edge, capture execution, and mutual transport layer security. Furthermore, CloudFront integrates with automated analysis dashboards that classify artificial intelligence bot traffic, helping you distinguish between benign search indexers and malicious scraping agents. When content changes at the origin, you must manage cache invalidation. Historically, invalidating cached items required submitting invalidation requests for specific URLs or wildcards. Recently, CloudFront introduced cache tagging invalidation. This feature allows you to attach custom tags to cached objects and submit a single invalidation request for a specific tag, instantly clearing all matching objects across the global edge network, regardless of their URL structures, which simplifies content management in headless architectures and data lakes. Resolving domain names and managing routing policies globally is the role of Amazon Route 53, a highly available and scalable domain name system service. Route 53 is designed to translate human-readable domain names into IP addresses. It supports several routing policies that let you control how traffic is distributed. Simple routing routes traffic to a single resource. Weighted routing distributes traffic across multiple resources based on assigned ratios, which is ideal for blue-green deployments and canary testing. Latency-based routing routes users to the region that provides the lowest network latency. Failover routing utilizes health checks to direct traffic to a secondary standby endpoint if the primary endpoint becomes unhealthy, enabling active-passive disaster recovery. Geolocation routing directs traffic based on the physical location of the user, which is critical for localizing content and enforcing regional compliance. Geoproximity routing directs traffic based on physical distance, allowing you to shift traffic from one region to another dynamically using bias values. Finally, multi-value answer routing returns multiple IP addresses in response to a DNS query, randomly distributing traffic and performing health checks to filter out unhealthy endpoints. Route 53 also provides secure DNS resolution for hybrid networks through Route 53 Resolver and Route 53 Profiles. Route 53 Resolver acts as a bridge, allowing your on-premises servers to resolve private hosted zones in AWS, and allowing AWS resources to resolve on-premises DNS names using inbound and outbound endpoints. Inbound endpoints allow on-premises systems to query Route 53 hosted zones, while outbound endpoints resolve on-premises domains by forwarding queries to local network DNS servers based on custom forwarding rules. Route 53 profiles simplify this management by allowing you to bundle private hosted zones, resolver rules, and VPC associations into a single profile and share it across multiple accounts using Resource Access Manager. For security, Route 53 supports DNSSEC, which signs your DNS records cryptographically to prevent cache poisoning attacks. To guarantee high availability during regional outages, Route 53 includes accelerated recovery configurations that provide a 60-minute recovery time objective, allowing public DNS records to be updated quickly during active regional service disruptions. To optimize network paths for applications deployed across multiple regions, AWS provides AWS Global Accelerator. While CloudFront accelerates static and dynamic web content using HTTP caching, Global Accelerator accelerates raw TCP and UDP traffic at the network layer. It provides you with static anycast IP addresses that route traffic to the nearest AWS edge location. From the edge location, Global Accelerator routes the traffic over the private AWS Global Network, bypassing the public internet entirely. This significantly reduces latency, packet loss, and network jitter, making it the ideal choice for real-time voice, video, financial APIs, and multi-region microservices. Global Accelerator also integrates with container workflows via load balancer controllers, allowing you to orchestrate global traffic routing directly within Kubernetes manifest configurations. Connecting your on-premises infrastructure to your AWS VPC requires choosing between physical fiber and encrypted tunnels. AWS Direct Connect provides a physical, dedicated network connection from your on-premises data center directly to an AWS facility. This connection bypasses the public internet entirely, delivering consistent, predictable network performance and high bandwidth, which is ideal for massive data migrations and continuous database replication. Direct Connect supports dedicated connections, which use physical fiber optic lines allocated exclusively to you, and hosted connections, which route traffic through a shared partner network. To route traffic to multiple VPCs across different regions using a single connection, you deploy Direct Connect gateways and configure transit virtual interfaces, or transit VIFs, to attach to transit gateways. Direct Connect supports link aggregation groups, or LAGs, which link multiple physical Direct Connect connections together to scale network bandwidth and redundancy. Direct Connect interfaces support enhanced CloudWatch metrics for border gateway protocol status, prefix advertisements, and prefixes received, helping you detect routing failures and manage prefix limits without custom monitoring scripts. If you require a faster, lower-cost setup, AWS Site-to-Site VPN establishes an encrypted IPsec tunnel over the public internet between your on-premises gateway and an AWS virtual private gateway or transit gateway. While VPN tunnels are secure, they are subject to the latency and performance fluctuations of the public internet. For remote user access, AWS Client VPN provides a client-to-site VPN service that allows remote employees to securely connect to resources in AWS and on-premises networks. Client VPN supports native attachment to AWS Transit Gateway, eliminating the requirement to set up a dedicated hosting VPC and allowing you to centralize your remote access architecture. By combining these networking components, architects implement a zero-trust network design. In this model, you do not trust any network location by default, even if it is inside your private subnet. Instead, you verify and encrypt every connection, manage network access control lists, enforce strict security groups, and authenticate all requests, securing your data flows across the global network. Securing your identity control plane and defending against advanced network threats brings us to Chapter 5, Security, Identity, and Compliance. In the cloud, identity is the primary security perimeter. Unlike traditional on-premises networks where physical firewalls protect servers, cloud resources are protected by logical access control systems. The fundamental service for managing identity is AWS Identity and Access Management, or IAM. IAM allows you to define who can access which resources under what conditions. It is built on 3 core entities: users, which represent physical people or applications; groups, which are collections of users sharing similar permissions; and roles, which are temporary identities assumed by users, services, or external identities. IAM enforces the principle of least privilege, meaning that you only grant the minimum permissions necessary for an identity to perform its job. To manage access, IAM utilizes policy documents written in JSON format. These policies come in 2 primary types: identity-based policies, which are attached directly to users, groups, or roles, and resource-based policies, which are attached directly to resources like S3 buckets or KMS keys. Resource-based policies are unique because they allow you to grant cross-account access, enabling identities in one AWS account to read or write to resources in another. To establish boundaries of control, you can configure permission boundaries. A permission boundary is an advanced policy that defines the maximum permissions that an identity-based policy can grant to an IAM principal. If a user is assigned a permission boundary, their effective permissions are the intersection of their identity-based permissions and the boundary, preventing developers from escalating their own privileges. You can also analyze permissions using IAM Access Analyzer, which uses automated reasoning to scan your resource policies and identify resources that are publicly accessible or shared with external accounts, helping you audit and enforce least privilege across your entire organization. Understanding how AWS evaluates these policy documents is critical for resolving access issues and passing professional exams. The AWS policy evaluation logic follows a strict flow to determine whether a request is allowed or denied. By default, all requests are implicitly denied. This means that if there is no explicit policy allowing a request, the request is blocked. When a request is evaluated, AWS searches for policies across 6 distinct layers: service control policies, which are organizational boundaries; resource-based policies, which are attached to the resource; identity-based policies, which are attached to the user or role; permission boundaries; session policies, which are passed during temporary role assumptions; and endpoint policies, which restrict traffic through VPC endpoints. During evaluation, if AWS encounters an explicit deny in any of these policy layers, the evaluation stops immediately and the request is denied, as an explicit deny always overrides any explicit allow. If there is no explicit deny, AWS looks for an explicit allow. For cross-account access, both the resource-based policy in the target account and the identity-based policy in the source account must explicitly allow the action. If either is missing, the request is denied under the default implicit deny rule. To enable federated access from external corporate environments, IAM supports OpenID Connect, or OIDC, and Security Assertion Markup Language 2.0, or SAML. Identity federation allows external users to authenticate using enterprise credentials, assuming IAM roles temporarily to access AWS resources without requiring local IAM user accounts. For mobile and consumer-facing applications, Web Identity Federation using Amazon Cognito manages authentication, coordinating with external social identity providers to assign temporary AWS credentials via Cognito identity pools. JSON policies support granular rule matching using the condition block. Conditions evaluate context keys using comparison operators, such as string equals, numeric less than, IP address, and date less than, to prevent privilege escalations and enforce resource boundaries. You can use multi-value operators like for any value or for all values. Policies support policy variables, which are runtime parameters that map variables like the caller's username or account ID directly to resource path prefixes, allowing you to write a single policy that secures private S3 folders for thousands of individual users. To enable secure, temporary access to your resources, IAM utilizes the AWS Security Token Service, commonly known as STS. When a compute resource or a user assumes an IAM role, STS generates temporary security credentials that consist of an access key, a secret key, and a session token. These credentials have a configurable expiration time, ranging from 15 minutes to 12 hours, reducing the risk of compromised credentials. To configure a role, you must define a trust policy and a permissions policy. The trust policy is a resource-based policy that specifies which trusted principals, such as a specific AWS service or an external identity provider, are allowed to assume the role. The permissions policy is an identity-based policy that defines what actions the assumed role can perform. When establishing cross-account access for third-party integrations, you must use an external identifier in the trust policy. The external identifier is a unique string that prevents the confused deputy security exploit, where a third party could be tricked into accessing your resources on behalf of another client. By requiring the third party to pass your unique external identifier during the Assume Role API call, you ensure that the transaction is authorized and secure. To centralize identity management across multi-account environments, you should use AWS IAM Identity Center. Identity Center allows you to manage user access to all your AWS accounts and cloud applications from a single location. It integrates with your existing identity providers, such as Microsoft Active Directory, Okta, or Google Workspace, allowing your employees to sign in with their corporate credentials. It also integrates with AWS Control Tower to automate the provisioning of permissions in new accounts. For root user accounts, AWS strictly enforces multi-factor authentication, requiring physical security keys or authenticator apps to mitigate credential theft. To protect data at rest, AWS Key Management Service, or KMS, provides a managed service to create, rotate, and control cryptographic keys. KMS supports symmetric keys, which use the same key for encryption and decryption, and asymmetric keys, which use a public and private key pair. Access to KMS keys is controlled using key policies, which are resource-based policies attached to the keys. To delegate key permissions programmatically to specific AWS services, you can configure KMS grants. A grant is a temporary, flexible permission structure used by services like Amazon EBS to attach encrypted storage volumes to EC2 instances, allowing the service to run cryptographic operations on your behalf, whereas key policies represent persistent, administrative access controls. KMS utilizes a design pattern called envelope encryption. In this pattern, KMS does not encrypt your large datasets directly. Instead, you call the KMS API to generate a data key. KMS returns a plaintext data key and an encrypted version of that data key. Your application uses the plaintext data key to encrypt your data locally, shreds the plaintext data key from memory, and stores the encrypted data key alongside the encrypted data. To decrypt the data later, your application sends the encrypted data key back to KMS, receives the plaintext data key, decrypts the data, and discards the key. This pattern minimizes network latency by keeping the data encryption local to your compute resource while maintaining centralized control over the master keys in KMS. When KMS keys are rotated, AWS maintains the older backing key versions to decrypt existing datasets, while using the new backing key version for new encryption operations, ensuring seamless key management without data migration. When managing keys, architects must understand the difference between customer-managed keys, AWS-managed keys, and AWS-owned keys. Customer-managed keys are created and managed by you. You have full control over their key policies, key rotation intervals, and deletion schedules, and you pay a monthly fee per key. AWS-managed keys are created automatically by AWS services on your behalf, such as when you enable encryption on an S3 bucket for the first time. You cannot modify their key policies, and AWS rotates them automatically. AWS-owned keys are part of a shared collection that AWS services use to secure metadata and internal resources. You do not pay for these keys, and you cannot view or manage them. If your compliance regulations prohibit storing keys on shared hardware, you can use custom key stores. A custom key store allows you to link KMS to a dedicated AWS CloudHSM cluster, which is a physical hardware security module single-tenant appliance, ensuring that your keys are stored on hardware that you control exclusively. For managing application secrets, API keys, and database credentials, AWS Secrets Manager provides a secure storage repository. Unlike KMS, which is strictly for cryptographic key operations, Secrets Manager stores sensitive text strings and automatically handles credential rotation. Secrets Manager manages rotation using secret versions and staging labels. OSCurrent, OSPending, and AWS PREVIOUS. During a rotation cycle, Secrets Manager invokes a custom Lambda function that executes a four-step rotation process. Creating a pending secret version, testing the pending secret version against the destination database, setting the pending version as active, and finalizing the rotation by updating staging labels, guaranteeing that database connections are never severed. Secrets Manager also supports multi-region secret replication, allowing you to replicate secrets automatically to secondary regions to facilitate disaster recovery workflows. If you need simple parameter storage without automated rotation features, Systems Manager Parameter Store offers a cost-effective, hierarchical storage system for configuration data and secrets, separating parameters into standard and advanced tiers based on size and throughput requirements. To defend your public-facing endpoints from malicious web traffic and distributed denial of service attacks, you will implement AWS WAF and AWS Shield. AWS Shield provides built-in DDoS protection. Shield Standard is enabled automatically for all customers at no charge, defending against common Layer 3 and Layer 4 attacks. Shield Advanced offers specialized protection, including real-time mitigation of sophisticated attacks, financial protection against scaling charges caused by DDoS spikes, and access to the AWS DDoS response team. AWS WAF is a web application firewall that lets you monitor HTTP and HTTPS requests forwarded to CloudFront, application load balancers, or API gateway. WAF allows you to write rules based on IP addresses, HTTP headers, query strings, and body content, blocking common web exploits like SQL injection and cross-site scripting. WAF includes managed rule groups and specialized dashboards that classify AI bot traffic, helping you rate-limit automated scraping agents while letting legitimate traffic flow freely. To detect threats and monitor runtime security across your accounts, AWS provides Amazon Guard Duty, AWS Security Hub, and Amazon Inspector. Amazon Guard Duty is a continuous security monitoring service that analyzes CloudTrail logs, VPC flow logs, DNS queries, and container runtime activity. Guard Duty utilizes machine learning and threat intelligence to identify suspicious behaviors, generating detailed findings classified by threat classes like Trojan, EC2, backdoor, EC2, and unauthorized access, IAM. These findings are mapped directly to the MITRE ATT and CK framework, allowing security teams to analyze threat vectors. Guard Duty runtime monitoring includes detections for sensitive file modifications on EC2, EKS, and ECS instances, helping security teams identify privilege escalation and persistence techniques in real time. Guard Duty can correlate multiple security events into attack sequences, mapping suspicious actions directly to threat frameworks to speed up incident response, triggering automated remediations using event bridge rules to isolate compromised virtual hosts. AWS Security Hub centralizes your security alerts and automates compliance checks. It aggregates findings from Guard Duty, Inspector, Macie, and partner solutions, presenting them in a unified dashboard. Security Hub compares your environment configurations against industry standards, such as the Center for Internet Security Benchmarks and the Payment Card Industry Data Security Standard, identifying security gaps and providing remediation steps. Amazon Inspector provides automated vulnerability management. It scans EC2 instances, container images in Amazon Elastic Container Registry, and Lambda function code for software vulnerabilities and unintended network exposure, helping developers identify and fix issues before code reaches production. To classify and protect sensitive data stored in S3, Amazon Macie utilizes machine learning and pattern matching to discover and inventory your data. Macie automatically scans S3 buckets for personally identifiable information, such as credit card numbers, social security numbers, and passport details. It alerts you if a bucket containing sensitive data becomes publicly accessible or is shared with accounts outside your organization. Finally, for compliance auditing, AWS Artifact provides on-demand access to AWS security and compliance reports, such as Service Organization Control Reports and ISO certifications, giving compliance officers the documentation necessary to verify that the AWS cloud infrastructure meets regulatory standards. In summary, establishing a secure cloud architecture requires a layered defense in-depth strategy. You secure your networking layer using VPC endpoints, private connections, and CloudFront OAC. You control access using IAM Identity Center, enforce MFA on root accounts, and manage granular permissions using IAM Access Analyzer and permission boundaries. You encrypt your data using KMS envelope encryption and rotate secrets automatically using Secrets Manager. Finally, You monitor your runtime environment for threats using Guard Duty, scan for vulnerabilities using Inspector, and audit compliance using Security Hub and AWS Artifact. With this comprehensive security foundation established, we are ready to explore the database engines that persist your structured and unstructured datasets. Persisting your data securely, efficiently, and at scale brings us to Chapter 6, Databases. A key decision for any system architect is choosing the right database engine based on the shape of your data and the requirements of your workload. AWS provides a wide range of database services, spanning relational databases, non-relational document stores, in-memory caches, graph databases, and specialized time series systems. Let us begin our database analysis with Amazon Relational Database Service, commonly known as Amazon RDS. RDS is a managed service that makes it easy to set up, operate, and scale relational databases in the cloud. It supports 6 popular database engines: MySQL, PostgreSQL, MariaDB, Oracle, Microsoft SQL Server, and Amazon Aurora. RDS automatically handles administrative tasks like software patching, database backups, host deployment, and hardware scaling, allowing developers to focus on schema design and query optimization. When designing relational databases, you must manage configuration parameters using DB parameter groups and DB option groups. A parameter group acts as a container for engine configuration values that can be applied to one or more database instances. Parameters are classified as either dynamic or static. Dynamic parameters are applied immediately without requiring a database reboot, whereas static parameters require you to initiate a manual reboot before the changes take effect. Option groups are used to manage optional features that are specific to certain database engines, such as enabling transparent data encryption in SQL Server or setting up Active Directory authentication in PostgreSQL. To scale storage dynamically, RDS supports storage autoscaling. You define a maximum storage threshold, and RDS automatically allocates additional storage space when the remaining free space drops below 10%, preventing database outages caused by disk space exhaustion. RDS supports multiple storage types, including magnetic, general-purpose SSD options like GP2 and GP3, and provisioned IOPS SSD classes like IO1 and IO2 Block Express, allowing architects to provision specific IOPS and throughput allocations. To identify performance bottlenecks, RDS provides performance insights. This feature visualizes database load by analyzing active sessions and correlating them with specific SQL statements, hosts, or users, helping developers pinpoint slow queries. RDS manages database backups using automated snapshots and manual snapshots. While you cannot encrypt an existing unencrypted RDS instance directly, you can achieve this by copying an unencrypted snapshot, enabling encryption options on the copy, and restoring the encrypted snapshot as a new database instance, transitioning data paths securely. When designing RDS databases for high availability, you configure a multi-AZ deployment. In a multi-AZ configuration, RDS automatically provisions and maintains a synchronous standby replica of your database in a different availability zone within the same region. When data is written to the primary database, the write operation is replicated synchronously to the standby instance. The write transaction is only confirmed to the application after both the primary and standby disks write the transaction log, guaranteeing absolute consistency. If the physical host fails, or if an entire availability zone experiences an outage, RDS automatically performs a failover. During failover, RDS modifies the canonical name record of your database endpoint to point to the standby instance, resolving the interruption in under 60 seconds with zero data loss. To scale read traffic, you can deploy read replicas. Unlike multi-AZ standby instances, read replicas utilize asynchronous replication. This means read replicas can experience replication lag if the primary database is subjected to heavy write volumes. Read replicas can be promoted to standalone primary databases, and they can be deployed across multiple regions to facilitate local read performance and disaster recovery failovers. For cloud-native relational databases, Amazon Aurora provides a fully managed relational database engine compatible with MySQL and PostgreSQL. Aurora completely redesigns the traditional database architecture by separating the compute layer from the storage layer. In Aurora, the storage layer is a virtualized SSD-based storage volume that automatically replicates your data across 3 availability zones, keeping 6 copies of your data. Aurora partitions this storage volume into 10 GB segments, known as protection groups. When data changes, Aurora replicates the logical changes directly to the storage nodes rather than writing complete transactional log files, reducing network traffic. The distributed storage volume is shared among all database instances in the cluster. Aurora handles writes by writing data to all 6 storage nodes in parallel, requiring a quorum of 4 out of 6 writes to confirm a transaction and a quorum of 3 out of 6 reads. This disaggregated storage design allows Aurora to scale storage capacity automatically up to 128 TB, healing itself by replacing degraded disks in the background without affecting database compute availability. For elastic workloads that experience unpredictable spikes in traffic, Amazon Aurora Serverless V2 scales database compute capacity up and down automatically in fractions of an Aurora capacity unit. This allows your database to handle sudden spikes in query volume instantly, and then scale back down to minimum capacity when the workload decreases, billing you only for the compute capacity consumed per second. To build globally distributed relational databases, Amazon Aurora Global Database replicates data across multiple AWS regions with typical latency of less than 1 second, allowing fast local reads and providing disaster recovery capabilities. Aurora Global Database supports write forwarding. This feature allows applications in secondary regions to send write operations directly to local read instances, which forward the write transactions to the primary database over private, high-speed AWS backbones. Aurora executes the writes, replicates the updates back to the secondary region, and updates local read caches asynchronously, simplifying global application design. For applications that require always-on availability, active-active multi-region writes, and PostgreSQL compatibility, Amazon Aurora DSQL provides a serverless distributed SQL database. Aurora DSQL disaggregates compute and storage across regions, allowing you to run distributed transactions with strong consistency and zero cold start times, eliminating the single point of failure inherent in traditional primary replica relational architectures. When your application requires single-digit millisecond latency at massive scale, relational databases become a bottleneck due to the overhead of enforcing schemas and managing tables. For these workloads, Amazon DynamoDB provides a fully managed, serverless, non-relational database service that delivers consistent, single-digit millisecond performance at any scale. DynamoDB is a key-value and document database, storing data as items with attributes. DynamoDB achieves its scale by partitioning data horizontally. When you write an item to DynamoDB, the service runs the item partition key through a hash function to determine exactly which partition to write the data to. As the size of your dataset grows, DynamoDB automatically splits partitions and redistributes the data, ensuring that read and write performance remains constant regardless of whether your table contains 1 gigabyte or 100 terabytes of data. To design efficient DynamoDB tables, you must understand the mathematical logic DynamoDB uses to allocate physical partitions. The system calculates partition allocations based on two primary limits: storage size and throughput. A single physical partition can store a maximum of 10 gigabytes of data. Furthermore, a single partition can support a maximum throughput of 1,000 write capacity units and 3,000 read capacity units. To determine the total number of partitions required for a table, DynamoDB calculates the storage partition requirements by dividing the total data size by 10 gigabytes. It also calculates the throughput partition requirements by dividing the total provisioned read throughput by 3000 RCU and the total provisioned write throughput by 1000 WCU. The system selects the maximum value from these three calculations and provisions that number of physical partitions. If your access patterns concentrate traffic on a small subset of partition keys, you will encounter hot partition issues, where a single partition exceeds its throughput limits and DynamoDB throttles the requests. To mitigate hot partitions, you can implement partition key sharding, which appends a random numeric suffix to high-volume partition keys, distributing write operations evenly across multiple partitions. You can configure DynamoDB throughput using provision capacity or on-demand capacity. Provision capacity requires you to define read capacity units and write capacity units, which is cost-effective for predictable workloads. On-demand capacity scales throughput automatically to handle traffic spikes, charging you per read and write request. To query data based on attributes other than the table partition key, you can create secondary indexes. A local secondary index uses the same partition key as the base table but a different sort key, sharing the table partitions and RCU and WCU allocations. Local secondary indexes must be defined when the table is created. A global secondary index uses a different partition key and sort key, can be created or deleted at any time, and has its own dedicated throughput capacity. To execute ACID-compliant operations across multiple items within or across tables, DynamoDB supports transactions. Transact write items and transact read items allow you to coordinate updates programmatically, costing twice the throughput of standard reads and writes. To capture data modifications in real time, you can enable DynamoDB streams or Kinesis data streams for DynamoDB. DynamoDB streams maintains a chronological log of changes for 24 hours, optimizing sequence processing using Lambda triggers. Kinesis data streams supports up to 1 year of log retention, allowing multiple consumers to parse the changes concurrently and integrate with third-party streaming engines. To cache frequently read items in memory, DynamoDB Accelerator or DAX provides a fully managed in-memory cache that reduces DynamoDB read latency from single-digit milliseconds to microseconds, utilizing write-through and write-around caching strategies to maintain consistency. Finally, to deploy multi-region, active-active databases, DynamoDB global tables replicate data asynchronously across regions, managing conflict resolution automatically using a last writer wins model. For other non-relational workloads, AWS provides specialized database engines. Amazon DocumentDB provides a fully managed document database compatible with MongoDB, allowing developers to run existing MongoDB code and queries on a scalable, secure architecture. For in-memory caching and real-time data stores, Amazon Elasticache manages Redis and Memcached clusters, offloading read-heavy queries from relational databases. For durable, in-memory performance, Amazon MemoryDB provides a Redis-compatible, durable database that stores data in memory while persisting transactions across multiple availability zones using a distributed write-ahead log. For graph databases, Amazon Neptune supports property graph and resource description framework models, allowing you to query highly connected datasets like social networks or fraud detection patterns, writing queries in Gremlin or SPARQL. For Cassandra workloads, Amazon Keyspaces provides a serverless, Apache Cassandra-compatible database. Finally, for time series data, Amazon TimeStream automatically scales to ingest and analyze billions of events per day, such as IoT sensor logs and application metrics, sorting data into memory and magnetic storage tiers to optimize performance and cost. Persisting your data in secure databases is only part of the software lifecycle. Managing code, builds, and deployments brings us to Chapter 7, Developer Tools and DevOps Part 1. To build modern, continuous integration and continuous delivery pipelines, you must understand the developer tools available within the AWS ecosystem. Historically, code repositories were managed using AWS CodeCommit, which remains a fully available managed source control service. CodeCommit supports standard Git operations, offering secure, private repositories integrated with IAM. CodeCommit provides native support for Git large file storage, allowing teams to store binary assets and large files directly inside their source repositories. CodeCommit repositories support automated triggers. You can configure a repository to send notifications via SNS or execute Lambda functions when code is pushed to specific branches, allowing developers to build custom automated checks, code auditing workflows, and notification integrations with collaboration channels. CodeCommit supports branch protection rules and pull request approval rule templates. These features allow platform engineers to enforce code review policies, requiring a specific number of approved reviews before code can be merged into critical branches, such as main or production. Access to repositories is controlled using IAM policies, which can enforce multi-factor authentication requirements for Git operations and restrict access using IP address conditions, securing source code from unauthorized modifications. You can integrate repositories with Amazon CodeGuru Reviewer. CodeGuru Reviewer uses machine learning and automated reasoning to scan your source code automatically during pull request reviews, identifying concurrency bugs, resource leaks, credential exposure risks, and deviation from AWS coding best practices, offering remediation recommendations. While organizations can choose to integrate their pipelines with external platforms like GitHub or GitLab using CodeStar connections, CodeCommit remains an active option for teams seeking a native, securely partitioned source repository within the AWS security boundary. To build and compile your source code, AWS CodeBuild provides a serverless build service. CodeBuild eliminates the need to provision or manage your own build servers. It runs your build scripts inside Docker containers, scaling automatically to handle parallel build tasks. You configure CodeBuild using a build specification file named buildspec.yml, placed in the root of your source repository. In the build spec file, you define the environment phases, environment variables, caching directories, and build commands. The build lifecycle consists of 4 main phases: The install phase, where you install runtimes and system packages. The pre-build phase, where you execute preliminary commands like logging in to Amazon Elastic Container Registry. The build phase, where you compile your code, run unit tests, and package your application binaries. And the post-build phase, where you perform cleanup actions and upload artifacts. To accelerate build times, CodeBuild supports local and remote caching. You can cache build dependencies, such as Maven or Node Package Manager packages, locally on the build container or remotely in an S3 bucket, preventing the need to download identical dependencies for every build. CodeBuild runs on diverse compute platforms, allowing you to choose x86 or ARM Graviton processor environments, and you can secure build environments by running CodeBuild containers directly inside your VPC, restricting access to private resources. You can configure CodeBuild to encrypt build artifacts using customer-managed KMS keys, and define IAM roles to grant the build environment permissions to publish Docker images to Amazon ECR or deploy packages to S3, automating build security. CodeBuild supports running custom container images from external registries and can be configured as a self-managed runner for GitHub Actions or GitLab pipelines, allowing developers to run containerized CI tasks on AWS compute resources. To automate code deployments to compute fleets, AWS Code Deploy provides a managed deployment service. Code Deploy can deploy applications to EC2 instances, on-premises servers, ECS tasks, or AWS Lambda functions. You configure Code Deploy using an application specification file named appspec.yml. The appspec file defines the application files to copy, the permissions to apply, and the lifecycle hooks to execute during the deployment process. The appspec hooks vary depending on the target compute environment. For EC2 and on-premises deployments, the lifecycle hooks include application stop, before install, after install, application start, and validate service. These hooks execute scripts that reside in your application bundle. Code Deploy supports multiple deployment strategies to minimize downtime. An in-place deployment updates the existing instances in a fleet one by one, which can cause temporary capacity reductions. A blue-green deployment launches a new fleet of instances, deploys the updated code, routes traffic to the new fleet, and terminates the old fleet, providing a safe rollback path if the deployment fails. You configure deployment configurations, such as one at a time or half at a time, to define the traffic shifting pace during in-place updates. For ECS and Lambda deployments, Code Deploy supports linear and canary deployments. A canary deployment routes a small percentage of traffic, such as 10%, to the new code version for a set period, monitoring health checks before shifting the remaining traffic, ensuring that bugs are detected before they impact the majority of users. For container deployments, Code Deploy manages traffic shifting by integrating with application load balancer target groups, modifying load balancer weights dynamically, and executing lifecycle hooks like before allow traffic and after allow traffic to run Lambda-based validation tests before shifting public traffic to the new task set, rolling back automatically if CloudWatch alarms indicate application errors. You can configure automatic rollback parameters, telling Code Deploy to immediately revert deployments to the previous working version if any connected CloudWatch alarm triggers, or if the deployment execution times out. Orchestrating these individual release phases into a continuous delivery pipeline is the role of AWS Code Pipeline. Code Pipeline allows you to visualize and automate the stages of your process. A pipeline consists of stages, such as source, build, test, and deploy, Each stage contains actions such as fetching code from a repository, running a build script in CodeBuild, running automated tests, and deploying the software using CodeDeploy. You configure pipelines to run automatically when code is pushed to your repository, and add manual approval actions to pause the pipeline until a team lead reviews the release. Code pipeline supports sequential and parallel execution of actions within a stage. The data passed between stages is stored as artifacts, which are zip files containing the application code, build files, and deployment configurations. These artifacts are stored in a dedicated S3 bucket managed by Code Pipeline. When data transitions between stages, Code Pipeline automatically zips the artifacts, writes them to S3, and retrieves them in the subsequent stage, maintaining data continuity across your delivery lifecycle. For multi-account architectures, you configure cross-account pipelines. This configuration requires you to encrypt the S3 artifact bucket using a customer-managed KMS key, allowing roles in target deployment accounts to decrypt and access the build artifacts, and establish trust relationships between the pipeline service role and target deployment roles, enabling secure cross-account deployment workflows. Code Pipeline supports cross-region release stages, automatically replicating build artifacts to S3 buckets in secondary regions, facilitating multi-region application deployment workflows. For platform teams seeking to standardize microservice delivery, AWS Proton provides a managed delivery service. Proton allows platform engineers to define environment templates, which specify the underlying infrastructure like VPCs and load balancers, and service templates, which define the container runtime and pipeline configurations. Platform teams write these templates using CloudFormation or the Cloud Development Kit. Developers then use these templates to provision their microservices through a self-service portal, ensuring that all applications across an organization conform to security, compliance, and operational standards. When a platform team updates an environment or service template, Proton alerts developers and automates the rollout of infrastructure updates, preventing configuration drift across enterprise teams. Finally, to manage application configurations dynamically, AWS App Config allows you to deploy configuration changes and feature flags to running applications without deploying new code. App Config validates configuration updates before deployment, rolls out changes gradually, and rolls back updates automatically if CloudWatch alarms are triggered, minimizing the impact of configuration errors. Developers configure validators in AppConfig, which can be JSON schemas or Lambda functions, to verify that the configuration content conforms to the expected structure. The deployment strategies in AppConfig define how configuration changes are rolled out over time, using growth factors and bake times to monitor application health metrics. If a configuration update causes an error, AppConfig automatically rolls back the change to the previous known good state, maintaining application availability. You can utilize the AWS AppConfig agent on ECS tasks or EC2 instances to cache configuration parameters locally, reducing API transaction latencies and protecting applications from configuration service outages. Defining and provisioning this infrastructure systematically brings us to Chapter 8, Developer Tools and DevOps Part 2. To achieve consistency and repeatability across your cloud deployments, you must replace manual console clicks with infrastructure as code. The core service for provisioning resources programmatically in AWS is AWS CloudFormation. CloudFormation allows you to define your entire infrastructure stack, including compute instances, databases, queues, and security groups, in a single text template written in JSON or YAML format. CloudFormation acts as a declarative engine. You specify the desired state of your resources, and CloudFormation determines the correct order of operations to provision them, managing dependencies and rollback procedures automatically if any resource creation fails. To build modular and scalable templates, CloudFormation supports nested stacks. Nested stacks allow you to define common infrastructure components, such as a standardized VPC network configuration or a security group baseline, as separate templates and reference them from a master root template. This design pattern bypasses the CloudFormation resource limit of 500 resources per stack, promoting reusability across engineering teams. You can configure stack policies to prevent accidental updates or deletions of critical resources, such as databases or storage volumes, during stack updates. To protect resources during stack deletion, you can configure deletion policies, choosing from delete, retain, or snapshot options to safeguard data volumes. CloudFormation supports stack termination protection, which prevents accidental deletion of the entire stack unless protection is explicitly disabled. To deploy resources across multiple AWS accounts and regions simultaneously, you can use stack sets. Stack sets integrate with AWS organizations, allowing you to deploy stacks to new accounts automatically as they are added to your organizational units. Before updating a stack, you can generate a change set, which shows you exactly what resources CloudFormation will create, modify, or delete, preventing accidental data destruction. CloudFormation also supports drift detection, which compares your running resources against the stack template, identifying manual changes made outside of the code pipeline. To extend CloudFormation capability to resources not natively supported, you can configure custom resources, which trigger Lambda functions to run third-party API calls, and utilize the CloudFormation registry to publish custom resource schemas. During EC2 provisioning, you configure helper scripts like cfn init to fetch configuration metadata, cfn signal to notify CloudFormation when application software is fully installed, and cfn hub to monitor metadata changes and apply configurations dynamically, orchestrating boot sequences. To write infrastructure templates using familiar programming languages, AWS provides the Cloud Development Kit, or CDK. The CDK allows developers to define infrastructure in languages like TypeScript, Python, and Java. When you compile your CDK project, it synthesizes your code into standard CloudFormation templates, which are then deployed via CloudFormation. The CDK is built on constructs, which are reusable infrastructure components. Constructs are organized into 3 tiers. L1 constructs map directly to individual CloudFormation resources. L2 constructs provide AWS-curated defaults, handling complex configurations like security group rules and IAM policies automatically. L3 constructs, also known as patterns, group multiple resources together into high-level architectures, such as a load-balanced ECS service running on Fargate. The CDK allows you to build custom, reusable construct libraries, enforcing organizational standards across all developer teams. Before deploying a CDK application, you must run CDK Bootstrap, which provisions the necessary AWS resources, such as S3 buckets and Elastic Container Registry repositories, to host the CDK assets, which are the local files, scripts, and Docker images that your infrastructure code references. CDK supports CDK pipelines, which is a high-level construct library that automates the deployment of multi-stack applications and manages CI/CD release stages programmatically. To interact with AWS services from your local machine, the AWS command line interface allows you to execute commands directly from your terminal. You can configure profiles to manage access keys, set region configurations, and write automation scripts. For application integration, AWS software development kits provide language-specific libraries to integrate your code with AWS APIs. The SDKs handle low-level tasks like HTTP requests, retry logic, error handling, and the AWS credential provider chain, which automatically searches for credentials in environment variables, configuration files, and IAM role metadata. When implementing retry logic in SDK clients, you must use exponential backoff and jitter. Exponential backoff increases the delay between retries exponentially, preventing the client from overwhelming downstream APIs. Jitter adds a random delay factor to the retry interval, choosing from full jitter or equal jitter algorithms, ensuring that multiple clients retrying failed requests do not call the service at the exact same millisecond, which avoids synchronized retry storm patterns and improves system stability, while connection pooling manages HTTP client timeouts and keep-alive settings to optimize throughput. Managing running servers and automating operations at scale is the role of AWS Systems Manager. Systems Manager provides a suite of tools to view and control your infrastructure. Session Manager allows you to open a secure terminal shell on your EC2 instances without opening inbound port 22 or managing SSH keys. Traffic is encrypted and routed through the Systems Manager API, and all user commands are logged to S3 or CloudWatch for auditing, fulfilling security compliance requirements. Session Manager supports port forwarding capabilities, allowing developers to establish secure local loops to database instances or run SSH tunnels through Session Manager. Security teams configure Session Manager profiles to enforce session duration limits and restrict user commands to pre-approved administrator commands. Systems Manager Run command allows you to execute shell scripts and configuration commands across a fleet of instances simultaneously, managing concurrency controls and error thresholds to pause operations if a high percentage of instances fail. Systems Manager State Manager automates the process of maintaining OS configurations, running association checks at scheduled intervals to install packages or configure security settings automatically. Patch Manager automates the process of scanning and applying operating system patches across your virtual machines based on custom patch baselines, patch groups, and maintenance windows. Parameter Store provides hierarchical storage for configuration parameters and secrets, supporting parameter versioning and parameter policies like expiration rules to manage parameter lifecycles. Parameter Store supports standard and advanced parameters, where advanced parameters increase size limits to 8 kilobytes and support parameter policies, whereas standard parameters limit allocation to 10,000 parameters per account. Finally, to govern multi-account environments, AWS Control Tower automates the creation of landing zones, enforcing organization-wide compliance using preventive guardrails, which are service control policies, and detective guardrails, which are AWS config rules, managing permissions across your entire cloud organization. Control Tower supports customizations for Control Tower, using lifecycle events to trigger Lambda configurations and automate resource deployment when new accounts are provisioned via the account factory. Designing application entry points for mobile devices, web browsers, and end users brings us to Chapter 9, end user, front end, and mobile. To deliver premium client-side experiences, cloud applications need robust hosting, rapid front-end integration, physical device testing, and scalable virtual desktop environments. Let us start our analysis with AWS Amplify Gen 2, which provides a code-first, TypeScript-driven development platform for building full-stack cloud applications. In Amplify Gen 2, developers define their database schemas, authentication workflows, and serverless backends using native TypeScript configuration files directly inside their front-end codebases. Amplify automatically provisions these backend services using the Cloud Development Kit under the hood, eliminating the need to write separate CloudFormation templates or use graphical console orchestrators. Amplify Gen 2 includes cloud sandboxes for every developer on the team, enabling them to test back-end modifications in isolated personal cloud environments that compile and deploy in real time. It also automates the creation of production, staging, and preview environments for each Git branch in your repository. For web hosting, Amplify supports modern frameworks like Next.js App Router with server-side rendering, deploying assets globally using CloudFront edge caches, and securing them using native web application firewall integrations to protect your front-end applications from malicious scripts and denial of service attacks. To optimize front-end hosting, Amplify Gen 2 integrates with Amazon Route 53 to manage custom domain names and SSL certifications, automating the creation of secure global endpoints. When hosting Next.js applications, Amplify automatically detects the framework features, configuring compute environments on AWS Fargate or Lambda to execute server-side rendering code, and caching static pages at CloudFront edge locations. This hybrid delivery architecture balances the dynamic capabilities of server-side rendering with the low latency and low-cost benefits of static site generation. For client-side data access, Amplify Gen 2 utilizes GraphQL APIs powered by AWS AppSync, allowing front-end code to query and mutate data using strongly typed queries. AppSync supports real-time data synchronization using WebSockets and manages local offline caches, ensuring that mobile and web applications remain operational and responsive when the client device loses network connectivity, syncing modifications back to the cloud database when the connection is reestablished, coordinating identity federation with Cognito user pools and Cognito identity pools. To resolve GraphQL queries efficiently, AppSync utilizes unit resolvers and pipeline resolvers. A unit resolver executes a single request and response mapping template against a specific data source, such as a DynamoDB table or a Lambda function. A pipeline resolver allows you to orchestrate multiple actions sequentially in a single API call, execution logic through separate functions, which is ideal for running authorization checks or data sanitization steps before writing to a database. AppSync supports API caching. You can enable server-side caching of GraphQL responses at either the whole API level or individual resolver level, configuring cache keys, caching sizes, and encryption keys to optimize query latencies. To ensure that mobile and web applications function correctly across a diverse fleet of client hardware, AWS provides AWS Device Farm. Device Farm is an application testing service that lets you test and interact with your mobile and web applications against real, physical smartphones, tablets, and desktop browsers hosted in AWS data centers. Instead of relying on software simulators or virtual emulators, which can fail to reproduce real-world performance bottlenecks and hardware bugs, Device Farm runs your automated tests on actual physical devices. You upload your test packages, written in automation frameworks like Appium or Selenium, and Device Farm runs them in parallel across dozens of physical devices, capturing video recordings, device logs, performance metrics, and screenshots. Device Farm supports desktop browser testing using Selenium grid configurations, allowing QA engineers to run web automation tests across Chrome, Firefox, Safari, and Edge browsers inside isolated VPC attachments, validating corporate firewall layouts. Device Farm supports two main modes of operation: automated testing and remote access. Automated testing allows you to run test suites concurrently across a customized device pool, generating comparative reports that analyze application performance and behavior across different operating system versions and hardware configurations. Remote access allows developers to open an interactive, real-time session with a specific device in the browser, manipulating the physical screen, installing debug builds, and simulating network conditions to troubleshoot customer-reported bugs directly. To secure the testing environment, Device Farm isolates each test run on a dedicated device that is physically wiped and factory reset after the execution completes, ensuring that sensitive application binaries and test data are never exposed to subsequent test runs. For corporate environments and remote workforces requiring secure, managed virtual desktop environments, AWS provides Amazon Workspaces. Workspaces is a fully managed, secure desktop-as-a-service solution that lets you provision virtual Linux or Windows desktops for your employees. Users connect to their workspaces using client applications from their personal laptops, tablets, or web browsers, receiving a high-performance desktop experience streaming over encrypted protocols. Workspaces integrates with your existing Active Directory to manage identities, and keeps all data stored securely inside your virtual private cloud, ensuring that sensitive corporate files are never stored on physical client devices. Workspaces manages profile persistence using AWS backup integration and profile unity features. For disaster recovery, you can deploy standby workspaces in secondary regions. Standby workspaces replicate user profiles and disk volumes automatically, allowing administrators to route users to the backup region during a regional service outage. For lightweight, managed endpoint deployments, Workspace's thin client provides low-cost hardware devices designed to connect remote employees directly to their virtual workspaces, reducing hardware procurement costs and simplifying workstation deployment for call centers and administrative staff. Workspaces utilizes high-performance streaming protocols, including the Amazon Workspaces Streaming Protocol and PC over IP, to compress and deliver the desktop display to the user endpoint. These protocols analyze network bandwidth and latency in real time, adjusting the video compression to deliver a smooth experience even over low-speed connections. From a security perspective, architects can configure Workspaces policies to disable local drive redirection, clipboard sharing, and local printing, preventing data exfiltration from the cloud network. Workspaces can be deployed in public subnets with internet access or private subnets that route traffic through an on-premises firewall via a VPN or direct connect link, allowing platform engineers to enforce strict corporate security controls on all virtual work environments. To stream legacy desktop applications to web browsers without deploying full virtual desktops, Amazon AppStream 2.0 provides a fully managed application streaming service. AppStream allows you to install your desktop applications on AWS hosts and stream their user interfaces directly to HTML5 web browsers on any client device. Platform engineers use AppStream Image Builder to create custom software images, compiling dependencies and installing applications on a golden host. AppStream supports two main fleet types: always-on compute fleets, which run instances continuously to deliver instant application startup times but incur higher costs, and on-demand fleets, which spin up compute instances dynamically when a user logs in, saving money but introducing a 2-minute startup delay. AppStream manages the underlying compute fleets, scaling the number of running application instances to match user demand, and maintains non-persistent user sessions, ensuring that files generated during a session are stored safely in an S3 bucket or shared EFS directory before the execution environment is destroyed. AppStream integrates with major identity federation standards, allowing users to sign in using single sign-on credentials, and supports custom network routing, allowing the streamed applications to access databases and APIs inside your private VPC. Orchestrating communication between these client-facing frontends and back-end microservices brings us to Chapter 10, Applications for Business. Modern enterprise applications require decoupled, asynchronous message routing and event-driven orchestration to handle millions of transactions without service degradation. Let us examine the tools available for business integration, beginning with Amazon Simple Email Service, commonly known as Amazon SES. SES is a cloud-based email sending and receiving service designed to send transactional messages, marketing notifications, and automated alerts at high volume. To maintain high deliverability rates and prevent emails from landing in spam folders, SES enforces email authentication standards, including Sender Policy Framework, Domain Keys Identified Mail, and domain-based message authentication, reporting, and conformance. SES allows you to warm up dedicated IP addresses gradually to build a strong sender reputation with major email clients, and provides monitoring tools to track bounce rates, complaint metrics, and delivery status logs. SES supports incoming email processing using receipt rule sets. You can configure rules to inspect incoming messages based on the recipient address and execute actions, such as saving the email to an S3 bucket, publishing a notification to an SNS topic, or triggering a Lambda function to parse the email body and extract attachment data. To control sending authorization across different AWS accounts, SES supports sending authorization policies. This feature allows you to grant permission to other IAM users or AWS accounts to send emails on behalf of your verified domain, ensuring that centralized marketing platforms can execute email campaigns while preserving security isolation. You configure IP address reputation filters to block or allow emails from specific IP addresses, and monitor the SES reputation dashboard to identify bounce rate trends. For pub/sub messaging, Amazon Simple Notification Service, or SNS, provides a fully managed, high-performance messaging service. SNS is built on a publish-subscribe model, where publishers write messages to a topic, and SNS automatically fan out the messages to multiple subscribing endpoints. Subscribers can include SQS queues, Lambda functions, HTTP webhooks, SMS mobile numbers, and push notifications. SNS allows you to write subscription filter policies, ensuring that each subscriber only receives the specific messages they are interested in, which reduces compute waste in downstream microservices. You configure SNS delivery status logs to track message delivery performance, logging details to CloudWatch to analyze delivery failures. SNS supports FIFO topics, which guarantee strict message ordering and deduplication when integrated with SQS FIFO queues, providing a secure method for executing transactional processes, such as financial transactions or inventory updates, across distributed container microservices. To manage delivery failures to endpoints like HTTP webhooks, SNS supports dead letter queues, allowing you to capture undelivered payloads for manual investigation. To queue messages and buffer workloads between distributed systems, Amazon Simple Queue Service, or SQS, provides a serverless message queuing service. SQS eliminates the complexity of managing message-oriented middleware, automatically scaling to handle virtually unlimited throughput. SQS offers two types of queues. Standard queues provide infinite throughput and guarantee at least once message delivery, but messages may occasionally arrive out of order or be duplicated. First in, first out, or FIFO, queues guarantee strict ordering and exactly once processing, but are limited in throughput capacity compared to standard queues. SQS limits message payload sizes to 256 kilobytes. To bypass this limit and transfer large payloads up to 2 gigabytes, you must use the SQS Extended Client Library. This library automatically writes the large payload to an S3 bucket, replaces the message body with a reference pointer, and reads the payload from S3 when the consumer retrieves the message, automating large payload management. To prevent multiple workers from processing the same message simultaneously, SQS utilizes a visibility timeout. When a consumer retrieves a message from a queue, SQS hides the message from other consumers for the duration of the visibility timeout. If the consumer processes the message successfully and deletes it from the queue before the timeout expires, the message is gone. If the consumer fails or crashes, the visibility timeout expires, and the message becomes visible to other consumers, ensuring no message is lost. To manage processing failures, you can configure a dead letter queue to capture messages that fail to process after a set number of attempts, isolating them for manual analysis. To minimize empty responses and reduce API transaction costs, SQS supports long polling, where the consumer request waits at the queue for up to 20 seconds for a message to arrive, rather than polling the queue continuously with empty requests. Orchestrating these individual messaging steps into complex workflows is the role of AWS Step Functions. Step Functions is a serverless orchestration service that lets you coordinate multiple AWS services into visual workflows called state machines. You write state machines using Amazon States language, defining steps as tasks, choices, parallel executions, or wait states. Step Functions automatically manages state transitions, retry policies, catch blocks, and execution history. It offers two types of workflows. Standard workflows are designed for long-running processes that can last up to 1 year, providing exactly once execution history and audit logs. Express workflows are designed for high-volume, short-duration tasks lasting under 5 minutes, providing high-throughput event processing at a lower cost, which is ideal for real-time APIs and IoT ingestion pipelines. Step Functions supports the map state, which runs a set of steps concurrently for each item in an input array. The map state has been enhanced with distributed map mode, which allows you to run high-concurrency child executions in parallel, processing up to thousands of data items from massive datasets stored in S3, making it the default orchestration pattern for big data and machine learning ETL pipelines. You configure error handling parameters, such as retriers and catchers, in individual tasks to define back-off intervals and fallback paths during workflow failures. For routing events across serverless microservices and integrating with third-party software, Amazon EventBridge provides a serverless event bus service. EventBridge uses rules to match events from AWS services, custom applications, and SaaS partner databases, routing them to targets like Lambda, SQS, or step functions. EventBridge includes EventBridge Scheduler, which lets you schedule millions of individual tasks and cron-like jobs across hundreds of AWS APIs, including automated tasks to scale Lambda-managed instances. It also includes EventBridge Pipes, which provides a serverless point-to-point integration resource to connect event sources like DynamoDB streams or SQS directly to targets, recently updated with native integrations for Amazon Managed Streaming for Apache Kafka, reducing the boilerplate code required to build streaming data pipelines. EventBridge Pipes supports filter expressions to discard unneeded events and enrichment steps that invoke Lambda functions or API gateway to modify payloads before routing them to destinations. EventBridge integrates with the EventBridge Schema Registry, which automatically discovers and registers event schemas, allowing developers to generate strongly typed code bindings for custom events. For orchestrating complex Apache Airflow data workflows, Amazon Managed Workflows for Apache Airflow, or MWAA, provides a managed orchestration service. MWAA automatically provisions and scales Airflow environments, letting you write directed acyclic graphs in Python to run ETL pipelines, coordinate machine learning training, and manage big data processes. MWAA manages DAG synchronization automatically, pulling Python files from a designated S3 bucket and updating worker environments. To integrate SaaS data sources without writing code, AWS AppFlow provides a secure data integration service that connects SaaS applications like Salesforce, Slack, and Zendesk to AWS storage and analytical services, transforming data formats and managing security keys automatically. You configure AppFlow flows to run on event triggers, scheduled intervals, or on demand, routing traffic through private network channels using VPC interface endpoints powered by AWS Private Link. Finally, to construct omni-channel customer service centers, Amazon Connect provides a cloud contact center service. Connect utilizes interactive voice response workflows and AI-driven speech analytics to analyze customer sentiment in real time, routing calls dynamically and integrating with databases and customer relationship management systems. Connect integrates with Amazon Lex, allowing developers to build natural language processing conversational chatbots that handle customer queries and resolve transactions automatically. Connect includes Amazon Connect Contact Lens, which analyzes voice and chat conversations in real time, extracting caller sentiment, detecting compliance policy violations, and alerting supervisors to negative customer experiences, optimizing customer support operations, orchestrating data, analyzing large data sets, and running machine learning models brings us to Chapter 11, Analytics and Machine Learning. To derive business value from raw data, cloud architectures require analytical engines that process batch datasets, manage streaming data, train predictive models, and deploy generative artificial intelligence systems. Let us begin our analytical review with Amazon Athena, a serverless query service. Athena allows you to run standard SQL queries directly on data stored in Amazon S3, using the metadata definitions stored in the AWS Glue data catalog. Because Athena is serverless, you do not provision or manage any database hardware. You are billed only for the volume of data scanned by your queries. To optimize costs and improve performance, Architects partition their S3 datasets and convert raw JSON or CSV files into columnar formats like Apache Parquet or ORC, which reduces the amount of data scanned and speeds up query execution. Athena supports query result reuse, which allows you to fetch cached query results for identical queries run within a specified window, eliminating redundant scan charges and improving application response times for dashboard workloads. To manage query execution and control costs across different developer groups, you can configure Athena workgroups. A workgroup allows you to isolate query histories, set hard limits on the volume of data scanned per query, configure custom S3 paths for query output files, and enforce encryption on query results using KMS keys. To query datasets stored in relational databases or external document stores directly without performing complex ETL migrations, Athena supports federated queries. This feature utilizes Lambda-based connector templates to execute queries on target databases, such as Amazon RDS or DynamoDB, and return the aggregated data directly to the user interface, unifying query pathways. For enterprise-scale data warehousing and business intelligence, Amazon Redshift provides a high-performance relational data warehouse. Redshift uses columnar storage, data compression, and zone maps to deliver fast query performance on petabytes of structured data. It offers Redshift serverless to scale compute capacity dynamically without manual cluster provisioning, and uses RA3 compute nodes to disaggregate compute from storage, allowing you to scale your analytical compute power independently of your persistent data volume. Redshift supports materialized views with automatic query rewriting and incremental refreshes, optimizing execution times for repeated dashboard queries. When scaling clusters, Redshift offers elastic resize, which automatically adds or removes compute nodes within minutes, compared to classic resize, which requires a full database copy. To share data across different business units, Redshift supports data sharing. This feature allows you to share live, read-only data across different Redshift clusters and AWS accounts without copying or moving the physical data, eliminating database duplication costs. To process massive datasets using distributed frameworks like Apache Spark, Hadoop, and Presto, Amazon EMR provides a managed big data platform. EMR automates the provisioning, configuration, and scaling of big data clusters, allowing data engineers to run complex ETL transformations, log analysis, and scientific simulations on elastic compute pools. EMR supports EMR instance fleets, which allow you to specify multiple instance types and purchasing options, combining spot and on-demand instances to optimize compute provisioning. EMR supports managed scaling, which automatically adjusts cluster sizes based on active workload metrics, and EMR serverless, which lets you run Spark and Hive applications without provisioning, managing, or scaling EMR clusters, paying only for the exact memory and vCPU resources your application consumes, and integrates with Amazon EKS to run Spark workloads on shared container fleets, simplifying platform administration. To catalog, clean, and transform your data automatically, AWS Glue provides a serverless data integration service. Glue includes a central data catalog that stores metadata about your S3 data, RDS tables, and external databases. It utilizes crawlers to scan your data sources automatically, determine data schemas, and write metadata definitions to the catalog. Glue also generates ETL code to transform and move data, and includes Glue Data Brew, a visual data preparation tool that lets data analysts clean and enrich data without writing code. Glue integrates with the Glue Schema Registry, which allows you to register and validate schemas for real-time streaming data pipelines, ensuring that data format variations do not break downstream analytics applications. You can coordinate multiple Glue crawlers and jobs using Glue workflows, creating complex, event-driven data ingestion chains that support cross-account catalog sharing via resource policies. For real-time data streaming, Amazon Kinesis provides a suite of services to ingest, process, and analyze streaming data at scale. Kinesis Data Streams allows you to build custom applications that process real-time telemetry, IoT logs, and clickstream data. It organizes data into shards, where each shard provides a fixed capacity of read and write throughput. A single shard supports 1 megabyte per second of write capacity and 2 megabytes per second of read capacity. To scale read performance for high concurrency consumers, Kinesis supports enhanced fan-out. This feature provides consumers with a dedicated logical pipe that delivers a throughput of 2 megabytes per second per shard using HTTP2 push protocols, eliminating read contention issues. To avoid data loss, you must monitor shard utilization and split hot shards that experience traffic spikes. Kinesis consumer applications utilize the Kinesis Client Library, or KCL, which manages work releases and tracks shard partition positions using DynamoDB, balancing workload processing across consumer hosts automatically. For near real-time delivery of streaming data to destinations like S3, Redshift, or OpenSearch, Kinesis Data Firehose provides a serverless delivery stream that automatically scales and transforms data formats before writing it to storage. Kinesis Firehose manages buffering using buffer size and buffer interval settings, grouping data packets before executing uploads to destination endpoints, and supporting custom prefix partitioning schemes. For real-time video capture and analysis, Kinesis Video Streams allows you to stream video securely from millions of devices for playback and machine learning processing. For managed Apache Kafka deployments, Amazon Managed Streaming for Apache Kafka, or MSK, provides a fully managed Kafka service that runs and scales secure clusters, eliminating the operational overhead of managing Kafka brokers, Zookeeper servers, and cluster replication, and supports MSK serverless to scale broker capacity dynamically in response to write throughput. For building, training, and deploying machine learning models, Amazon SageMaker provides an end-to-end machine learning platform. SageMaker includes SageMaker Studio, an integrated development environment for data scientists to write code, train algorithms, and manage pipelines. It features SageMaker Canvas for building machine learning predictions using a visual interface and supports automated pipeline orchestration, feature store management for storing machine learning features in low-latency online and high-capacity offline stores, and model endpoint deployment on serverless or dedicated instance fleets. When deploying SageMaker models, you must choose from 4 deployment options. Real-time endpoints are designed for latency-sensitive applications requiring dedicated, running virtual machines with GPU acceleration. Serverless endpoints scale compute dynamically to handle traffic bursts, bypassing the need to manage instance fleets but introducing cold starts. Asynchronous endpoints queue incoming requests, accommodating large payload sizes up to 1 gigabyte and automatically scaling down to 0 compute capacity when the queue is empty. Batch transform endpoints run offline predictions on massive S3 datasets, provisioning compute instances dynamically and terminating them when the inference process completes. Generative artificial intelligence has updated the ML landscape, led by Amazon Bedrock, a serverless service that provides access to foundation models from AWS and leading AI startup companies. Through Bedrock, developers access foundation models like the Amazon Nova family, Meta Llama, and Anthropic Claude using a unified API. Bedrock includes Amazon Bedrock Agent Core, which serves as the primary orchestration layer for deploying autonomous agents. Agent Core analyzes production execution traces to provide visibility into agent intent, failure patterns, and decision trajectories. It also integrates web search and browsing policies to ensure agents can retrieve real-time information safely. To secure these interactions, Bedrock guardrails allow you to define content filters and block personally identifiable information, while knowledge bases automate retrieval-augmented generation by linking foundation models to vector databases. Finally, for developer environments, AWS provides Kiro, a purpose-built agentic development environment designed for spec-driven development. Kiro replaces legacy assistant plugins, allowing developers to define structured requirements that Kiro uses to autonomously plan, implement, and verify code changes across your software repositories. Monitoring your resources, auditing compliance, and governing costs brings us to Chapter 12, Management and Governance. A resilient cloud environment requires continuous visibility, automated configuration tracking, landing zone governance, and tight financial management. The core service for real-time monitoring and operational visibility is Amazon CloudWatch. CloudWatch collects and tracks metrics, which are variables that represent the health and performance of your resources, such as CPU utilization on EC2 instances or latency on application load balancers. Metrics are organized using namespaces, metrics names, and dimensions. A dimension is a name-value pair that is part of the metric identity, and when you retrieve metrics or set alarms, you must specify the exact dimensions used to publish the data. CloudWatch supports high-resolution custom metrics, which can be published at 1-second intervals, allowing real-time monitoring of critical microservices, compared to the standard 1-minute or 5-minute intervals of default AWS metrics. You can create metrics alarms to monitor these variables and trigger automated actions, such as sending notifications via SNS or initiating auto-scaling policies. When metrics exceed defined thresholds, alarms support multiple actions, including EC2 actions like rebooting, terminating, stopping, or recovering degraded virtual host instances, and auto-scaling actions to scale compute fleets horizontally. Alarms operate in 3 states: OK, alarm, and insufficient data. You configure alarms by defining evaluation periods, such as requiring a metric to exceed a threshold for 3 out of 5 data points, and specifying how the alarm should treat missing data points, choosing from breaching, not breaching, ignore, or missing options to prevent false positives. CloudWatch supports composite alarms, which combine multiple metric alarms using Boolean logic. For example, you can create a composite alarm that only triggers if both CPU utilization is high and application response latency is degraded, reducing alarm fatigue by preventing alerts during transient spikes. Composite alarms support alert suppression, allowing you to suppress alarms on downstream services if a parent infrastructure component, such as an application load balancer, is already unhealthy, streamlining incident response for operations teams. CloudWatch also aggregates application and system logs, allowing you to run complex SQLite queries using CloudWatch logs insights to troubleshoot bugs and scan log patterns in seconds. Logs Insights supports commands like fields, filter, stats, sort, and limit, enabling engineers to parse multi-gigabyte log groups and extract latency metrics or error rates. To convert raw text logs into actionable metrics, you can configure metric filters, which scan incoming log streams for patterns, parsing parameters like response times, and writing numeric data to custom metrics. You can also configure subscription filters to forward logs in real time to destinations like Amazon Kinesis data streams, AWS Lambda, or Amazon OpenSearch service for real-time analysis and indexing. For user experience monitoring, CloudWatch Synthetics creates canary scripts that mimic user interactions with your web applications, verifying API endpoints and front-end rendering paths from different global locations. CloudWatch includes AWS Evidently, which allows you to run feature flagging, A/B experiments, and rolling launches, calculating performance variation metrics across different application deployments. To monitor application dependencies and microservice linkages dynamically, CloudWatch Application Signals automatically discovers and visualizes service maps, letting you define service-level objectives and track performance bottlenecks across distributed systems, integrating natively with AWS X-Ray to provide trace-level visibility into distributed application request chains. To profile network connectivity and monitor public client latencies, CloudWatch Internet Monitor tracks routing performance from client networks to your AWS resources, helping you identify public network carrier anomalies and optimize global data paths. To record API calls and track changes across your AWS infrastructure, Amazon CloudTrail provides a continuous auditing service. CloudTrail records every API call made in your AWS account, including the identity of the caller, the time of the request, the source IP address, the request parameters, and the response elements. These events are saved as logs in an S3 bucket or sent to CloudWatch logs. CloudTrail classifies events into 3 categories: management events, which capture administrative operations like creating or deleting resources; data events, which record read and write operations on S3 objects, DynamoDB items, or Lambda functions, capturing granular data access paths; and insights events, which use machine learning to detect anomalous API volumes or changes in your baseline administrative activity. You can configure a multi-region trail to aggregate logs from all regions, or an organization trail to centralize logging across all accounts managed by AWS organizations. To protect the integrity of these logs, CloudTrail supports log file validation. When enabled, CloudTrail generates cryptographic digest files that contain SHA-256 hashes and RSA signatures of the log files, allowing security auditors to verify mathematically that the logs have not been modified or deleted. Security teams encrypt CloudTrail S3 buckets using customer-managed KMS keys and apply strict resource policies to restrict write access to the CloudTrail service principal, establishing S3 lifecycle policies to transition historical logs automatically to Glacier Deep Archive to optimize storage costs. To track configuration changes and evaluate resource compliance automatically, AWS Config provides a continuous monitoring service. Config maintains a detailed configuration history for all supported AWS resources, showing how a resource configuration has changed over time. It evaluates these configurations against config rules, which are predefined or custom validation rules. Config rules can be configured to run on configuration changes, which evaluates resources in real time as modifications occur, or on a periodic schedule, which runs compliance scans at set intervals. You can implement custom config rules by linking the rule to an AWS Lambda function, which parses the resource configuration payload and returns compliance signals. For example, you can enable a config rule to verify that all S3 buckets block public access. If a developer manually updates a bucket configuration to make it public, AWS config marks the resource as non-compliant and can trigger automated remediation actions using Systems Manager automation documents, such as immediately reverting the bucket permissions to private. To aggregate compliance data in multi-account environments, you can configure config aggregators, which collect configuration and compliance metrics from multiple AWS accounts and regions into a single dashboard, integrating with AWS organizations to simplify governance for security operations teams. To manage approved catalogs of IT services, AWS Service Catalog allows platform engineers to define, govern, and distribute cloud templates to developers. Service Catalog enables self-service provisioning, ensuring that developers can deploy approved resources like pre-configured databases or secure developer environments without violating organizational compliance rules. Service Catalog resources are organized into portfolios, which are collections of products, which are CloudFormation templates. Platform teams can share portfolios across accounts using Resource Access Manager. To enforce compliance, platform teams define launch constraints, which use specific IAM service roles to provision resources, allowing developers to deploy infrastructure without needing permissions to create those resources directly, which enforces the principle of least privilege. For managing software licenses from vendors like Microsoft, Oracle, and SAP, AWS License Manager helps you track and control license consumption across your EC2 instances and on-premises servers, preventing license compliance violations and reducing software costs. License Manager integrates with Systems Manager to track license consumption on on-premises virtual machines via SSM Agent. License Manager allows you to set up rules that block instance launches if vCPU or core license allocations are exceeded, automating contract compliance. To evaluate your cloud architectures systematically, the AWS Well-Architected tool provides a self-service assessment engine. The tool guides you through a review of your workloads against the 6 pillars of the Well-Architected Framework, generating an improvement plan with prioritized recommendations to optimize reliability, security, and performance. To track, analyze, and optimize your cloud spend, AWS Billing and Cost Management provides a suite of financial governance tools. AWS Cost Explorer allows you to visualize and analyze your historic and forecasted costs, filtering expenditures by service, tag, or account. Cost Explorer includes anomaly detection, which uses machine learning to monitor your daily spend patterns and alert you to unexpected cost spikes. AWS Budgets lets you set custom cost and usage limits, triggering automated email alerts or actions when your actual or forecasted spend exceeds your budget thresholds. Budget supports budget actions, which allow you to configure automated responses, such as applying restrictive IAM policies, shutting down test instances, or executing Systems Manager automation documents when a budget threshold is breached, preventing runaway billing costs. For granular, raw billing data, cost and usage reports deliver comprehensive CSV or Parquet datasets to S3, detailing hourly resource usage and billing metrics, which can be analyzed using Athena or QuickSight. Finally, for organizations managing complex multi-tenant billing models or external client billing, AWS Billing Conductor allows you to apply custom pricing rules, distribute credits, and generate custom invoices, simplifying the financial reconciliation of cloud resources by creating custom billing groups and custom pricing plans for individual business units, defining custom markups, discounts, or credit distributions. Migrating legacy workloads and transferring data to the cloud brings us to Chapter 13, Migration and Transfer. For large organizations, transitioning on-premises data centers to AWS requires systematic discovery, continuous replication, and secure data transfer mechanisms. Let us begin our migration analysis with Migration Evaluator, a service designed to discover your local server inventory and build a business case for cloud migration. Migration Evaluator installs agentless collectors in your on-premises virtualized environments, communicating with VMware vCenter, Microsoft Hyper-V, or physical bare metal servers. The collectors track CPU, memory, and storage utilization over time, gathering runtime telemetry to build a granular profile of your infrastructure. It then generates a cost estimate comparing your local operating costs against optimized AWS compute configurations, factoring in licensing models like bring your own license to help financial officers plan budgets, and choose the appropriate EC2 instance sizes before the migration begins. Integrating with AWS Migration Hub to track discovery metrics across your migration dashboard. To execute the migration of virtual and physical servers systematically, AWS Application Migration Service provides a block-level continuous replication tool. Application Migration Service installs a lightweight replication agent on your source servers, which copies the contents of their local disks to lightweight staging instances in your AWS VPC. The replication agent reads data at the sector level, encrypting the blocks and streaming them over secure TCP port 1500 directly to the staging area. This staging subnet contains low-cost replication instances and EBS target volumes that maintain a continuous, block-level sync without disrupting source application operations. The migration lifecycle involves distinct stages: ready for testing, test in progress, ready for cutover, and cutover execution. During the testing phase, you launch test instances in an isolated subnet to verify application startup scripts, network configurations, and driver compatibility without affecting source production workloads. When you execute the final cutover, Application Migration Service automatically converts the replicated disks into native EBS volumes, provisions EC2 instances matching the target configurations, installs guest operating system drivers, and redirects network routes, minimizing application downtime to minutes. Application Migration Service supports post-launch actions. This feature allows platform teams to automate operational tasks upon launch, such as running custom configuration scripts, upgrading guest operating system versions, installing systems manager agents, and executing security validation tests automatically. To migrate relational and non-relational databases with minimal operational impact, AWS Database Migration Service, or DMS, provides a managed replication service. DMS supports homogeneous migrations, where the source and target database engines are the same, such as migrating an on-premises PostgreSQL database to RDS PostgreSQL. It also supports heterogeneous migrations, such as migrating Oracle to Aurora PostgreSQL, by utilizing the schema conversion tool to rewrite schemas, store procedures, views, and database triggers. The schema conversion tool automatically converts source database schemas into target-compatible SQL files, highlighting code compatibility issues that require manual refactoring. The DMS replication instance acts as the compute engine that connects to both the source and target endpoints, and you can deploy these replication instances in multi-AZ configurations to prevent failures during long-running migrations. When configuring DMS tasks, you must optimize large object, or LOB settings. DMS supports 3 LOB modes. Limited LOB mode, which allocates a fixed buffer size for LOB columns to optimize performance. Full LOB mode, which transfers LOB data of any size but runs slower due to separate query processing. And inline LOB mode, which combines the performance of limited mode with the flexibility of full mode by transferring small lobs inline with table data. To verify migration correctness, you can enable DMS data validation. This feature compares rows in the source and target tables, calculating data block hashes and logging mismatch errors, helping you detect data corruption before cutover. Source database replication requires specific configurations, such as enabling supplemental logging in Oracle or setting up replication slots in PostgreSQL, ensuring that the DMS replication instance can read transactional logs without interruption. For transferring massive volumes of offline data to AWS, the AWS Snow family provides physical hardware appliances that bypass network bandwidth constraints. Snowcone is a small, rugged device offering up to 14 terabytes of storage, designed for edge data collection and transfer. Snowball Edge is a larger appliance available in storage-optimized and compute-optimized configurations, providing up to 100 terabytes of capacity and local EC2 compute capabilities, making it ideal for mobile military deployments or industrial data gathering. Compute-optimized Snowball Edge devices include local virtual CPUs and graphics processors, allowing you to run containerized applications and EC2 instances to process data in remote, disconnected environments before shipping the hardware back to AWS data centers. Snowball Edge devices incorporate a Physical Trusted Platform Module, or TPM, chip to establish a hardware root of trust, protecting data with full disk encryption and featuring self-destruct mechanisms that erase cryptographic keys if the chassis is physically compromised. Snowball Edge supports local clustering, allowing you to link multiple devices together to scale local storage and compute resources dynamically at the edge. For exabyte scale migrations, Snowmobile consists of a ruggedized shipping container pulled by a semi-truck, capable of carrying up to 100 petabytes of data, providing physical data transit to AWS data centers when network uploads would take years to complete. To automate online data transfers between local storage and AWS, AWS Data Sync provides a secure, agent-based transfer service. Data Sync installs a virtual machine agent in your local environment, connecting to local file systems via NFS or SMB, and streams data over encrypted connections directly to S3, EFS, or FSX. Data Sync accelerates transfers by optimizing network bandwidth, utilizing parallel processing streams, and compressing data during transit. Data Sync includes task execution modes that allow you to verify data integrity by checking all data, checking only transferred data, or verifying file hashes at the source and target, ensuring that metadata, directory structures, and file permissions are copied with absolute fidelity. You can configure data sync tasks to run on demand or on a scheduled cron-like interval, automating continuous file replication to S3 storage classes or EFS file shares. Finally, for managing file transfers with external partners, the AWS Transfer family provides a managed service to host SFTP, FTPS, and FTP endpoints in AWS. Recently updated with support for Applicability Statement 2, or ASTU, protocols. Transfer family stores incoming files directly in S3 or EFS, integrating with IAM or custom identity providers to manage user access. You can configure Transfer family to use custom identity providers by routing authentication requests through API Gateway to a Lambda function, which validates credentials against an external Active Directory or database. You can configure Transfer Family to use ACM to bind custom domain names and manage SSL certifications, and select TLS cipher suites that conform to corporate compliance standards. You can configure Transfer Family to trigger automated post-upload processing pipelines using receipt workflows. For example, when a partner uploads a CSV file via SFTP, the Transfer Family can trigger a step function state machine or a Lambda function to process the file content, validate the data schema, and write records to a DynamoDB table, automating enterprise integration workflows and sending ASTU message disposition notifications back to the partner. Designing these migration and operational architectures according to established best practices brings us to Chapter 14, AWS Well-Architected Framework. To build cloud systems that are secure, high-performing, resilient, and cost-effective, architects must evaluate their designs against the 6 pillars of the Well-Architected Framework: operational excellence, security, reliability, performance efficiency, cost optimization, and sustainability. The operational excellence pillar focuses on running and monitoring systems to deliver business value and continuously improving processes. Key design principles include performing operations as code, making frequent, small, reversible changes, refining operational procedures frequently, anticipating failures, and learning from all operational events. Platform teams implement these principles by defining infrastructure using CloudFormation and the CDK, which allows resources to be versioned, tested, and rolled back systematically. Operational procedures are documented in Systems Manager automation documents, ensuring that operational tasks are executed consistently and can be refined over time based on feedback from post-incident reviews. Platform teams utilize runbooks, which document step-by-step procedures for routine operational tasks, and playbooks, which outline specific troubleshooting steps to resolve system anomalies. Post-incident analysis templates ensure that teams conduct thorough root cause reviews after service disruptions, documenting lessons learned and translating them into automated checks. Engineers run simulated game days to inject failures into test environments, verifying that auto-scaling groups and backup failovers function as expected, preparing the organization to handle real-world service disruptions. The security pillar focuses on protecting information, systems, and assets while delivering business value through risk assessments and mitigation strategies. Core design principles include implementing a strong identity foundation, enabling traceability, applying security at all layers, automating security best practices, protecting data in transit and at rest, keeping people away from data, and preparing for security incidents. Architects enforce these principles by utilizing IAM Identity Center to federate user credentials and apply the principle of least privilege. Organizations deploy multi-account structures, isolating production, staging, development, and security audit workloads in separate accounts managed by AWS organizations. Traceability is established by enabling CloudTrail logs and VPC flow logs across all accounts, piping events to CloudWatch for continuous auditing. Data protection is achieved by encrypting S3 buckets and EBS volumes using KMS envelope encryption, managing encryption keys, and rotating credentials automatically. To keep people away from data, platform engineers build automated CI/CD pipelines to deploy software updates, eliminating the need for developers to log directly into production instances using SSH or remote desktop protocols. Security teams use SSM Session Manager to execute diagnostic commands on EC2 instances, logging session commands to S3 for auditing while maintaining a tight security boundary. The reliability pillar focuses on ensuring a workload performs its intended function correctly and consistently when expected. Key design principles include automatically recovering from failure, testing recovery procedures, scaling horizontally to increase workload availability, stopping guessing capacity needs, and managing change through automation. You implement reliability by deploying multi-AZ database configurations, utilizing auto-scaling groups to replace unhealthy compute instances, and implementing loose coupling using SQS and event-driven architectures. Reliability requires you to balance fault tolerance against high availability, accepting the cost of redundant infrastructure in secondary zones to guarantee uninterrupted service during local facility outages. A key design pattern for reliability is the bulkhead pattern, where you isolate application components into separate pools of compute and storage resources, ensuring that a failure in one microservice, such as a traffic spike on a reporting API, does not cascade and degrade other critical user flows, maintaining broad application availability. Engineers test recovery procedures by injecting simulated failures, such as network partitions, physical rack outages, or database failovers, into staging environments, validating that failover systems execute correctly. When designing distributed communication, architects enforce retry policies with exponential backoff and jitter, alongside circuit breakers and rate limiting to protect downstream services from overload during recovery cycles. The performance efficiency pillar focuses on using computing resources efficiently to meet system requirements and maintaining that efficiency as demand changes and technologies evolve. Core design principles include democratizing advanced technologies, going global in minutes, using serverless architectures, experimenting more often, and considering mechanical sympathy, which means aligning your software design with the underlying cloud hardware. You achieve performance efficiency by selecting Graviton 5 processors, which deliver better performance per watt compared to traditional architectures. Architects select storage technologies that align with access patterns, utilizing S3 Express 1 zone to deliver single-digit millisecond latency for machine learning training datasets, and leveraging serverless compute with Lambda to scale execution environments horizontally in response to incoming events, optimizing performance throughput. Caching architectures, including CloudFront edge caches and ElastiCache in-memory clusters, are deployed to offload read traffic and reduce database processing latencies. Mechanical sympathy requires developers to understand the virtualization layer, tuning network threads and memory structures to align with the guest instance capacity. The cost optimization pillar focuses on avoiding unnecessary costs and running systems at the lowest possible price point. Key design principles include implementing cloud financial management, adopting a consumption model, measuring overall efficiency, stopping spending money on data center operations, and analyzing attribution of expenditure. You optimize costs by configuring auto-scaling fleets to match compute resources to user demand, and purchasing savings plans or reserved instances for steady-state workloads to secure deep discounts. Savings plans offer flexibility across compute resources, including EC2, Fargate, and Lambda, committing to a specific hourly spend in exchange for reduced rates. Architects utilize AWS Compute Optimizer, which analyzes server utilization metrics using machine learning to recommend right-sizing options for EC2 instances, EBS volumes, and Lambda functions. Platform teams configure policies to identify and delete orphan resources, such as unattached elastic IP addresses or stale EBS snapshots, ensuring that resources are only provisioned when active. Architects implement S3 lifecycle policies to archive cold data to cheaper storage classes like Glacier Deep Archive, and utilize Cost Explorer to identify and eliminate cost anomalies. Platform teams establish tagging strategies to allocate cost metrics to individual applications, analyzing attribution using cost and usage reports parsed with Athena to build FinOps dashboards. The sustainability pillar focuses on minimizing the environmental impacts of running cloud workloads. Key design principles include understanding your impact, establishing sustainability goals, maximizing utilization, adopting new, more efficient hardware and software offerings, using managed services, and reducing the downstream impact of your cloud workloads. You implement sustainability by migrating workloads to shared serverless platforms like Lambda and Fargate, maximizing resource utilization, and selecting energy-efficient processors like the Graviton family, which reduce power consumption per compute cycle compared to traditional architectures. Platform teams optimize EKS worker node utilization using Carpenter, which consolidates container workloads on fewer, larger instances during low traffic windows to reduce idle power consumption. You can optimize data storage by implementing compression formats, eliminating duplicate files, and configuring policies to expire old logs. Platform teams establish tagging strategies to allocate resource footprints to individual applications, optimizing data structures to minimize persistent storage sizes. You can track your carbon footprint using the Customer Carbon Footprint tool, analyzing your environmental impact and designing architectures that support long-term ecological balance. By combining the 6 pillars of the Well-Architected Framework with the physical reality of the global infrastructure, you can confidently design, deploy, and govern cloud architectures that scale to handle any workload in the modern digital landscape.